Okay, so let's start. I have to follow to find where was the last slides from yesterday. So today we will keep discussing about the RTE. So if you remember yesterday, we were basically discussing how we can arrive to the radiative transfer equation from basic principles, just using classical physics, basically. And then you saw that we could write the radiative transfer equation like this here, where you have only absorption terms, there is no emission terms here, okay? And then I was telling you that this propagation matrix K can be decomposed in several contributions, how to say, in an absorption matrix, in a decurrence matrix, and a dispersion matrix, which contains the different contributions from the absorption and dispersion and so on. Okay, so we will see some properties of this propagation matrix today, and then we will see how we can add the source terms in the radiative transfer equation, which are missing here. This is only the absorption part of the radiative transfer equation, okay? And then we will change it a little bit just to make it applicable to the solar atmosphere, okay? Just in a few changes. So, and we will also introduce a very basic concept, which is the local thermodynamic equilibrium, okay? So everything we will discuss in the following days relative to radiative transfer in these first lessons will be always within the local thermodynamic equilibrium approach, okay? In Uitenbroek, we will discuss later the effects of non-local thermodynamic equilibrium in the radiative transfer equation. But we will just keep LT in our case, okay? So we can have a look to some properties of this propagation matrix just to understand how the transfer occurs, okay, through the atmosphere. Well, I don't remember, I think Kevin didn't introduce yesterday the concept of Muller matrices, but probably he will talk about that today. And the point is that this propagation matrix has also the same properties as these Muller matrices, okay? So in particular, this propagation matrix, the intensity and this relation always hold. This is because light is partially polarized, okay? Remember, when light is totally polarized, this is just unequal here, okay? And these four matrix elements are important because they just constitute the so-called attenuation and the polarizance vectors, and they are responsible for the variation of the total intensity of the light beam, and also are responsible for the increase or decrease of the degree of polarization in the system, okay? So we can actually do some math, and we can write down this inequality and put it in as a function of the absorption profiles, okay? And then that's easy to do, the math. You can realize that this expression is just depending on the different absorption coefficients, okay? So the only way to get these three elements equals 0 actually is when we are in a system that is isotropic, okay? So there is no variations on the refractive index in any of the directions. In such a case, in the isotropic case, all these parameters are equally 0, okay? This one of the properties of the polarization propagation matrix, and then there are other properties. For instance, it can be demonstrated that there are two quantities which are independent on the reference system where you define the Stokes parameters. Actually, these two quantities are independent on the reference system and independent on the azimuth value of the reference system, okay? So this is also important to keep in mind for the future. Other properties that this matrix, this propagation matrix has is regarding the variation of the polarization degree along the ray path, okay? So let me try to explain what is this all about. So we can define just a function, for instance, which is written like this, which is the intensity minus the other Stokes profiles. We can write it as like this, where P is the polarization degree, okay? And then we can try to understand how is the variation of the polarization degree, how is the variation of this function, new function, with optical depth, with Z, okay? And you do the math, you will realize that the variation is just basically this, okay? It just depends on the first component of the propagation matrix, okay? You solve this equation, you reach this solution, and it means that the function f, which is related to the polarization degree, always decreases exponentially from the initial value, okay? You go to the bottom of the atmosphere and then do the radiative transfer, you will see that the variation of f is decreasing exponentially, okay? We can put these results in terms of the polarization degree, and we have actually this new expression here. And if you try to analyze this expression more in detail, you would realize that there are some results, okay, that you can really write down from there. No? So the first one is that no matter the initial degree of the polarization, okay, if the medium has a constant tau I, okay, the beam is always completely polarized, okay? It doesn't change. Actually, if the polarization degree is unity, the light also stays completely polarized, whatever the value of the propagation matrix is, okay? Other conclusion that you can draw from this expression is that the absorption and dispersion processes are not depolarizing, okay? So that the polarization matrix, the propagation matrix, sorry, is a sufficient condition for the medium to be non-depolarizing. And the other property that you can write down is that the polarization effects can appear in the transport of radiative energy through emission processes. And these emission processes has been neglected so far, okay? In the radiative transfer equation, as we know it so far, we haven't included these emission processes. So, and this is what we have to do now. We have to include those emission processes, okay? So, well, this radiative transfer equation only accounts for absorption and dispersion effects. And to fully understand the variation of the Stokes vector along the path, we have to add the emission properties of the medium, okay? And basically what we do in practice is we add an additional term, which is this J here, which is a 4 elements vector, into the radiative transfer equation. So we just add it here, okay? And I will explain why we do so, okay? Well, and actually this is the radiative transfer equation, including both source and source terms and emission terms with the propagation matrix. And this equation just describes how the radiation behaves. Well, this equation really accounts for all infinitesimal subtraction and addition of Stokes profile through the atmosphere. So the radiative transfer equation is actually a differential equation. It's a simple differential equation, so it's not very difficult to solve in principle. It can be seen as a system of 4 differential equations which are coupled, one for each Stokes profile, okay? But it cannot be solved, it has to be solved altogether. So you cannot solve the equation for a single SOX profile. You have to include the 4 of them just to solve the equation, okay? This radiative transfer equation includes everything. Also here in this particular expression, is very difficult to distinguish which are the terms that account for absorption processes, the terms that account for emission processes, and also for processes like scattering in the media, okay? Everything can be included here, okay? So usually when we talk about the absorption processes, so basically it's an exchange of energy between the different processes because it has to be in equilibrium. So it's what we were discussing yesterday, the radiative transfer equation. This can be seen as the sinks and the sources have to be in equilibrium, okay? But this absorption and emission processes depend on the local values of the medium, of the thermodynamic variables, and the scattering depends on the radiation field. Okay. Well, in summary, the radiative transfer equation is really a non-linear differential equation, and what we are looking for actually is a description of the variation of the Stokes profiles here. Once we know how which are the material properties of the atmosphere and the status of the radiation field, okay? So for that, we really need to know the so-called statistical equilibrium equations. I don't know if you have heard about them. And actually, the solution of the radiative transfer equation has to be seek together with the solution of the statistical equilibrium equations. So you have to solve both problems simultaneously. And this is a very big problem, so it's not easy to solve. And what we are going to do here is to try to solve this equation in the so-called local thermodynamic equilibrium, which is a very important approximation. In local thermodynamic equilibrium is very important and it's very helpful for many astrophysical plasmas and for many astrophysical applications, okay? So, because this approximation can explain the formation of many spectral lines, especially in the solar photosphere and in other stars, okay? So, the basic assumption of a local thermodynamic equilibrium is that the radiation, and only radiation, is the one that is allowed to deviate from thermodynamic equilibrium, okay? So if we do so, is in the thermodynamic equilibrium of the system just depends on the local values of the temperature and the gas density, okay? We need to assume also that the local distribution of velocities is Maxwellian, okay? And that the number of absorbers and emitters in the atmosphere is basically governed by the so-called Boltzmann and Saha equations, okay? Under these assumptions, we can verify that this Kirchhoff law actually is fulfilled, okay? The Kirchhoff law is very important because basically what tells us is that the emission and absorption has to be in equilibrium, okay? And this is very important. In that situation, we can write down the emission terms, as you can see here, which depends on the Planck functions, basically, okay? So this is the black body function here, which depends just on frequency and temperature, and then we can plug the source function into the RTE, and what we have actually is the expression of the radiative transfer equation in local thermodynamic equilibrium. Well, the good thing of this Kirchhoff law is that the emission term and the absorption term have exactly the same shape, okay? And this is what we fulfill just setting the emission term equal to the Planck function, okay? The emission terms only include the first row of the propagation matrix, just because those are the ones related with intensity. That's normal. This emission is just only just intensity. Okay, and also it's important to keep in mind that the emission is partially polarized. Okay. Well, with this equation, we can actually try to go further and write down the radiative transfer equation in a different form. Okay. And well, I wanted to say something here, but I was missing the point. Okay, because well, I think I will go directly here because I wanted to discuss something about the implications of departing from LT, but I think this is something that probably we will understand later. Okay, so what I wanted to show is that in summary, we have this expression for the radiative transfer equation when a light beam goes through a plane parallel or stratified medium. Okay, and you can basically see the Stokes vector here, the propagation matrix, and then the source function is just given by the Planck function here. And this is the compact form of the radiative transfer equation. What we are going to do now is to see in practice some solutions, simple solutions to the RT in local thermodynamic equilibrium, so you can understand how it works, how it looks like, and how can you understand this equation in simple scenarios. Okay, so before that, we can write this radiative transfer equation in a more appealing form for radiative transfer, okay, for the stellar atmosphere. And we will first consider that the propagation matrix can be decomposed in a propagation matrix related with the continuum intensity and a propagation matrix related with the line with the line transfer. Okay. If we take this into account, we can just write down the propagation matrix in the continuum as with the absorption coefficient here. Okay. Where this is just the frequency independent absorption coefficient for the continuum. Okay. And in the other hand, the propagation matrix related with the spectral lines can be written in this way, where this function here, if you remember, is the absorption, represent the absorption and dispersion profiles of the system, okay, of the medium, okay. So, and remember, this is the oscillator strength of the line, and these two functions are given by the Voigt and Faraday functions, okay. You do these changes, and then you write down the propagation matrix like this, okay, where this line to continuum absorption is given by this ratio. Then you end up with a new expression for the radiative transfer equation, which is the one that we usually solve in the computer, okay? So, but before continuing, I want to introduce the concept of the continuum optical depth, which is very important for radiative transfer, okay? The continuum optical depth is just the integral along the path of the absorption coefficient, okay? It is measured in the opposite direction of the propagation of light, and the origin is in tau z equals 0, which sets the bottom of the atmosphere, okay? It's there where light starts to go through the solar atmosphere. When the opacity, so the absorption, the continuum optical depth is equal to 0, is when we set the the scale height, so the height of the atmosphere equals 0, okay, in practical calculations, okay. Also, the optical depth is the number of mean free paths between the outermost boundary, so the top of the atmosphere, and Z, okay. This optical depth is very important, and you will see that this is very useful in practice when you analyze spectropolarimetric data, okay? So when we have introduced all these concepts, we can write down the radiative transfer equation in terms of the optical depth instead of writing that down in terms of the height, okay? This is much more useful in practice. And then the equation is like this, and then you have all the different coefficients here, the propagation matrix, where you see the different absorption and dispersion profiles, and also you see these two angles that so far they are the colatitude and the azimuth of the system, okay? Well, we can continue and try to solve this equation in particular scenarios, okay? So this is the first case, and this is probably the more interesting case. What happens if the medium is just isotropic? If the medium is isotropic, we know that the different absorption and dispersion profiles, okay, they are all the same. If they are all the same, we know that these coefficients in the propagation matrix, they are identically 0, okay? And then the RT simplifies a lot, okay? So this, because this happens. Well, actually the propagation matrix becomes diagonal, and the system of 4 equations, which is just decoupled, and then you have one equation for each Stokes parameter. You have one equation for Stokes I, one for Stokes Q, U, and V, okay? So actually you can write those equations like this here, no? in the same format. Well, usually this equation is called in some textbooks as the equation for polarized light, but this is actually not really valid, no? Because this can be said only when the light is actually unpolarized. So Q, U, and V is equal to 0, okay? But in this equation, you cannot just generate Q, U, and V because actually there is no source terms. The only source terms is in Stokes I, okay? And that's really important, but there are 4 equations. There are other 2 particular cases which are very important to understand. One of them is when the ray path coincide with this direction, okay, or with the Z direction. In that case, the colatitude angle is equal to 0 or 90, okay? In that particular case, the propagation matrix elements can be cast at least. So you can see that these ones are equal to 0 and these ones are just simplified. And also you will realize that these other elements can are the negative, okay? If you look at these equations, you would realize that the dispersion absorption profiles in one of the directions just disappeared from the equation, okay? Well, you can write down this equation just with the propagation matrix, and the propagation matrix would look like this, okay? And the point is that to understand why these 2 absorption and dispersion profiles have disappeared is because light polarized along this vector direction can actually not propagate along that direction, okay? Because the electromagnetic waves are just transversal to the propagation direction, if you remember. Okay, and then the equation it can be written like this, okay? Then in this situation, when the light propagates through that direction, only the only couple differential equations are those related with the Stokes I and V, and those related with the Stokes Q and U, okay? They are just separated, and you could solve both independently, okay? But since, again, there is no source force involving Q and U, if the light is originally unpolarized, then you cannot produce linear polarization in this situation, okay? You just have Stokes I and V. You have intensity and circular polarization, okay? Actually, what you have is two independent scalar equations in this situation, which relates Stokes I and V, intensity and circular polarization, okay? What's the meaning of this? So the meaning is that if the light is originally unpolarized, only circular polarization can be originated if the ray path coincides with the optical axis, okay? So imagine now that instead of being the propagation along the principal direction, it is orthogonal, no? Then the colatitude could be now different. It would be half P, okay? And then if we fix the azimuth to the medium, we have that the different elements of the propagation matrix can be cast as these ones, as this, okay? So you can also do some calculations and then write down again the RTE, and you will see that these off-diagonal elements of the propagation matrix are 0. You can try to write down this equation slightly different way to see much better the results, and then rotate the reference system by a negative azimuth angle, okay? And then you will see that the sum of the elements of the propagation matrix remains the same, but others change, like here, like this way, okay? And then the RTE can be cast like this, okay? You can see that this propagation matrix, actually, you have the off diagonals here and here equals 0. And in this particular case, when the propagation is transversal, we have now the couple I and Q in the one hand and U and V in the other hand, okay? So, which is different from before. And again, since there is no source terms in U and V, okay, U should be equal B equals 0, okay? And they should remain the same through the medium. The only two different from 0 are just I and Q, okay? And that means that the only, in this situation, the light beam can only be linearly polarized if it is originally unpolarized, okay? Well, these two different solutions are difficult to have in mind right now, but you will see that it is really related on how linear polarization and circular polarization works when you have a magnetic field in the medium, okay? And these are just a simple examples for the RTE. And you have also to remember that we haven't yet introduced any magnetic field here. So this radiative transfer equation is built upon the characteristics of the medium. So well, how do we just update the radiative transfer equation to take into account the magnetic field? Okay, how we change it? Is it this equation valid when we have a magnetic field, or it is not? Okay. So in this chapter, what we want to do is just basically to write the RTE when we have a magnetic field in the atmosphere. And for that, we will do several things, and you will see that some of them are counterintuitive, okay? Because everything we have been discussing do not include magnetic fields, okay? Well, we have actually formulated the RTE for an anisotropic media in local thermodynamic equilibrium, okay? Let's remember that. Now we will just check how it looks like in the case when you have magnetic field in the atmosphere, okay? But for convenience, and all of a sudden, we will assume that the media is isotropic, actually, not anisotropic. It will be now isotropic. You remember that we were just a few minutes ago discussing the solution of the equation when the medium is isotropic. But most of the elements in the propagation matrix are just zero, okay? But when we introduce a magnetic field in the media, it is the magnetic field itself, the one that introduces the anisotropies in the medium, okay? So, and this is so because it just introduces a preferential direction for the radiation, okay? Just to understand that, we will discuss how the magnetic field acts in the atmosphere, just from the Lorentz model, okay? And then we will see that this classical explanation of the magnetic field can give an explanation to this so-called normal Zeeman effect, but it does not explain the so-called Alon-Monod-Zeeman effect. That one you can only explain if you derive the RT from quantum mechanics, okay? And then we will learn how these spectral lines, how the lines split into different Zeeman components, and how we can do the real transfer, the RT, when we have a magnetic field, and then see the splitting of the lines and different line transitions and so on, okay? So, but the first thing is just to try to understand what happens when you put a magnetic field in your system. Well, again, we assume that the medium is now isotropic. It's not anisotropic anymore. And then we just put a magnetic field. When you put a magnetic field in the system, you have to basically take into account the second Newton law, and for each of the components of the electric field and so on, and then find a solution for that equation. And we were discussing for the dispersion and absorption profiles, okay? If you do so, you arrive at the same results. Actually, you arrive at the conclusion that the absorption and dispersion profiles has to be cast in this way, as if the media were anisotropic, as we discussed. But now, because of the presence of the magnetic field, but in this case, the anisotropy is just introduced by the magnetic field, okay? So let's assume that the magnetic field is aligned with this E0, just because of convenience, okay? And then we know that when we have a new force on the electron, this force can be written like this, which is the Lorentz force, okay? This is the vector product. This assumption is completely general, okay? There is no, this is completely general, and the medium is still an isotropic, okay? So with this assumption, we can really see that if the light is polarized along a given direction, then light would be linearly polarized along the magnetic field lines, okay? If the light is polarized along the other two directions, then we will have right-handed and left-handed circular polarized light, okay? In a plane which is perpendicular to the magnetic field vector, okay? In this case, you can find out that the different components of the Lorentz force can be written like this. And then you can introduce that in the equations that we were discussing yesterday and write down the absorption and dispersion profiles in the presence of a magnetic field, okay? If you do so, you find the solution for the absorption and dispersion profiles, which is actually this one. And you can see here that we have not taken into account the quantum mechanics effects yet, or the book velocity, or the thermal turbulent velocity, and so on. But this is still the absorption and dispersion profiles that we were discussing, okay? But what's the difference here now with the equations when the media is just anisotropic? So you can realize that just the real and imaginary parts of the refracting index is not now related with the conductivity or the permeability. Now is related with the resonance frequencies of the electrons in the presence of a magnetic field, okay? And these frequencies can be written as a central frequency here plus the Larmor frequency, okay? Well, you can see this, just you have to look at the equations, okay? This is the Larmor frequency, this is the frequency of the transition, basically, plus alpha multiplied by the Larmor frequency in the transition, and then we can just define these quantities for the Zeeman wavelength splitting. I can see that, okay? And at the end, you can express numerically which is the splitting of the line due to the presence of a magnetic field in terms of the magnetic field itself and with respect to the central wavelength of the transition, okay? Well, again, if we introduce all the quantum mechanical effects and the the turbulent motions and the macroscopic velocity of the plasma, we can write down the equations for the dispersion and absorption profiles. They still are the same, but right now you have these two elements here, which are now related with the presence of an magnetic field, okay? Well, now, in the presence of a magnetic field, the important thing to notice is that the absorption and dispersion profiles split in three different components, which are shifted in wavelength, okay? The three components are the right-handed circular component, okay, which is shifted to the red, to longer wavelengths. You have a linear component, which is along the magnetic field and is centered. This one is not shifted. And you also have another component, which is left-handed circular, okay, which is shifted to the blue, which is shorter wavelengths, okay? And actually, the greater the magnetic field, the greater the longer the wavelengths and the greater the splitting, okay? This can be clearly seen here, no? So for longer wavelengths, the splitting of the lines due to the magnetic fields is actually larger. This is why usually when we go to infrared lines, it's much easier to measure fields because we can see the splitting of the lines for smaller fields. When we are at the blue, it's very difficult to see how the line splits due to the presence of a magnetic field, okay? This is just because the splitting is proportional to the wavelength and to the magnetic field itself, okay? Well, Actually, this is what I was telling you. So that the amount of splitting is a direct diagnostic, actually, of the magnetic field itself. Okay. Well, if we label these three components as the red component and the blue component and the principal component, we can just write down the elements of the propagation matrix like this, where you have the principal component, the blue and the red component, and then we can name now these two angles instead of the colatitude. We can talk about the inclination of the magnetic field with respect to the Z component in the Cartesian system, okay? And this one, we can name it still the azimuth of the system, okay? Well, in practice, this is how these different components act. So you can see, for instance, that in one of these elements that they are made from three different absorption profiles, and the absorption profiles will be placed at different positions depending on the splitting of the magnetic field. So the principal component would be at the center. The red and blue components would be in different sides, okay? And the combination of these three profiles would give rise to the different elements of the propagation matrix. And then the relationship between all of them will give rise to the shape of the Stokes profiles, okay? In this case, you can see also the form of the absorption profiles. In this case, remember that the dispersion profiles are looking like this, an asymmetric profile, okay? Well, what happened when you just look at these propagation matrix elements when you use two different magnetic field strengths? You can see actually here very easily that the ones in the dashed line is a magnetic field which is small, and you can see that when you increase the magnetic field, the different profile split, okay, linearly with the magnetic field strength, okay, and then the combination of them give rise to the Stokes profiles, okay. Actually, one thing that you can see from this diagram is that the propagation matrix have clear symmetry properties, okay? So these profiles are symmetric around the central frequency, okay? Some of them are positive or negative symmetry, okay? Well, this actually a summary of what we have been discussing, okay? We have just changed the labeling of the different absorption and dispersion profiles in a convenient way, just to understand how the light is polarized, okay? And you can see that when for instance, the colatitude, now the inclination of the field is equal to 0, so the magnetic field is pointing towards the observer, and then the central components P and just vanish, and there is no linearly polarized light along the propagation direction, okay? When the inclination of the field is basically 90 degrees, these two components, they contribute if they are linearly polarized, okay? Okay, so the next slide is we'll talk about different properties about how we actually compute these different spectral lines and so on. So far, if you have any question regarding all this part, it would be the right moment, I think. No question.
So when you were talking about propagation metrics and before introducing source terms, if I understood correctly, propagation metrics will not depolarize light. It will only increase polarization, but it's reversed for the source terms, or?
Can you say it louder, a little bit louder?
Okay. So when you're talking about propagation metrics, you said that propagation metrics will not depolarize light. It will only increase polarization.
Mm-hmm.
And source terms can decrease polarizations.
Mm-hmm.
Okay.
Okay. So I think maybe we can stop here or something for a break, or this is too early? No. Okay. Yeah. Oh.
So if you, just one announcement, if you haven't seen on the Discord, I posted the links to the Python notebook that we will use at the end of the afternoon for the Milne-Eddington exercises, and also a link to the data pointed to in that notebook. So if you want to go follow along on your computer, then please download both of those so that you can do the exercise.
And I have another one that I forgot to say earlier, but I got a new version of David's slides up in the drive, and it's only one file for the whole week. I'll probably update it again tomorrow or whenever he makes any tweaks, but I'll let you know. So every day we'll have a final version of the slides for the whole week.
Okay, so I think it was too fast actually before. So you have questions about regarding anything, because I got a couple of questions, and I think maybe there are some things that are unclear, so we can go through some of the concepts again. Okay, so basically remember that what we have done now is starting from the RTE, which was derived from classical physics, basically. We had no source terms there, okay? And we needed to add these source terms just to put it in basically in equilibrium, no? Because just to follow Kirchhoff's law, okay? And what we have done now is to take the RTE actually in the isotropic configuration, configuration, which is actually where when the propagation matrix is diagonal, and then add a magnetic field in the system, which is then the responsible one for the anisotropies, okay? And then we find out that we recast all the absorption and dispersion profiles. We have the same expression, basically the same expressions, but now the different splittings of the different profiles in frequency depends on wavelength and on the magnetic field strength itself, okay? So it's very important, but the RTE is formulated in the isotropic case, not in the anisotropic case, okay? The one that makes it anisotropic is the magnetic field, the presence of a magnetic field. So these concepts are difficult to understand. And I want also you to remind, and you have all the material there, that the different solutions that we have been taking into account, that is when the magnetic field is pointing toward the observer, so it's aligned with the line of sight, the solution of the RTE can be decoupled, okay? In the 4 equations, you have 2 equations. One of them are for stocks I and V, and these are the only ones that are related with the source function. Okay, so this is the only one that makes sense to solve because Q and U is just identically zero, okay, because there is no emission term. And in the other way, when the magnetic field is perpendicular to the surface, we can decouple the equation and we have just that Stokes B is basically coupled with Q or U, and then I and Q are in a different system. So it's only I and Q, the equations that make sense, because these equations are the only ones that are connected to the source term, okay? In that case, Q and V would be identically zero. Well, it could be Q or U or different. It depends on the azimuth, okay? Because if you change the azimuth or rotate the azimuth in a different way, you can couple I and U instead of I and Q, okay? So it depends. But these two configurations are important because they are easy solutions just to understand how the transfer is done, how the propagation matrix changes, and you can easily see how are the different contributions to Stokes IQ, U, and V, looking at the different elements of the propagation matrix, okay? So remember that now we have also write down the propagation matrix with the three components, and we have called them principal component, okay, red component, and blue component, depending on the strength of the magnetic field, which is the one now responsible for the splitting, for the different absorption and dispersion profiles, okay? But these classical formalisms can only explain three components: the blue, the red, and the principal one, okay? And if you know some atom physics, you know that a spectral line splits when you have a presence of an magnetic field, but this splitting can be in three components or in many other components, okay? So you can have not only three, but many more. This is the so-called anomalous Zeeman effect, okay? So this cannot be explained from the classical point of view, just using the simple derivation from the Larmor frequency and the Lorentz force and so on, okay? And for explaining those things, you have to use actually quantum mechanics. But what we can do is just to update the radiative transfer equation to take into account that you can have the possibility of splitting, which is has multiple components, okay? And this is what I want to explain now here, okay? And for that, I don't know if you all know, all of you, quantum mechanics, or at least the concepts of quantum mechanics. So I'm not going to explain anything related to quantum mechanics, but I want just to show some basic concepts about quantum mechanics in 2 slides, so you can understand how the splitting takes place when you have a particular spectral lines, okay? I know it wasn't this one. So this is what I was telling you, that the Lorentz model itself only explains Zeeman triplets, but not multiplets, okay? And for that, we need a quantum mechanic treatment. We are not going to do that treatment here. I want to explain you how things are modified when you take that into account, okay? And well, for those that doesn't know anything about quantum mechanics, you know that the electronic state of an atom basically can be uniquely take care, because this uniquely is very dangerous. This is too short to explain really this, but it can be really identified with the atom angular momentum, which is L, and with the electron spin angular momentum, which is S, okay? In an atom made of N electrons, okay? When I say uniquely identified is when we are in one of the known coupling possibilities of the angular momentum. Okay, we have to couple the spin and the orbital angular momentum, and there are only 2 ways to do that, okay, theoretically. One is the LS coupling, which is the one that we usually use in stellar atmospheres because most of the lines can be well explained under LS coupling. And there is another coupling, which is the JJ coupling, okay, which is for lines usually that has heavy elements basically, okay. So only in these two situations, these two quantum numbers can precisely give the configuration of the status of the electrons and the atom itself, okay? When we are in this LS coupling, we can actually add the spin angular momentum and the atom angular momentum separately, okay? And we have this L and S uppercase, and then we can talk about the total angular momentum, okay, which is J, which is L plus S, okay? We know that we can actually, with three quantum numbers, we can specify the status of the electronic state of the atom itself, okay? With the electronic state of the atom, we can identify the energy levels and the energy of the atom, okay? And then we can really identify atomic transitions and things like that, okay? So usually what we use is the spectroscopic notation. If you haven't seen this before, you have here the spectroscopic notation, okay? And from there, we can really see how the line splits and so on and so forth under LS coupling. In any other situation, usually the state of the atom is not uniquely identified, okay? It's much more complex than that. Well, this is what I was telling. If we have LS coupling and we have a given electron configuration that we can know with the spectroscopic notation because we have the three quantum numbers, we can actually identify the energies involved in all the electronic transitions, okay? And all these electronic transitions are the ones that produce absorption and emission of a photon, okay? Which is important. Not all combinations are possible, okay? There are rules in quantum mechanics, okay? This, I'm not going to go through why we have these rules and so on, but the only thing that we have to know is that we have, in all these transitions, we have always to conserve angular momentum, okay? And if you do so, you have to fulfill these rules here, okay? And this will tell you which transitions are allowed when you have a specific configuration. Now, what happens when you have an atom and then you expose it into an external magnetic field, like in a stellar atmosphere? Well, you know, the system state, the state of an atom is given by its Hamiltonian, okay? When you introduce a magnetic field, you have to add an additional component, an additional term to this Hamiltonian, and then solve the system, taking into account this new term, okay? When you do so, you use just a perturbation analysis in quantum mechanics just to arrive to a solution, okay? But the only thing that you have to know is that this solution is the one that will provide you how the atom splits, basically in the presence of the magnetic field, okay? Well, in summary, if you want to go through these details, I recommend you to go to one of the a good textbook, okay? Where you can find all the derivations and all the concepts. But basically, when you have an external magnetic field, you have only particular levels that give rise to the different components, okay? These components depends on the quantum numbers, okay? For instance, if you have an atom which has a specific quantum number, J, you can have different atomic transitions, and depending on them, you can have transitions that fulfill this condition, where the quantum number M, which is the one related with the magnetic field, is just 0 or plus minus 1, okay? And the three different values of the magnetic quantum number M are the ones that are related with the different transitions in the so-called pi component, okay, which is the P component, the Celtran component, and also between the sigma B and sigma red components, which are related with the left-handed and right-handed circular polarization, okay? So I will show you a diagram that you can see much better how this works in practice, okay? So imagine that you have an atomic transition where you have a lower level with G equals 0, okay? And then J equals 0, and then an upper level with J equal 1, okay? So the J equals 0 can only have one split line when you have a presence of an magnetic field, which is corresponding to MJ equals 0, okay? However, the level with J equal 1 can split in three different sub-levels, okay? It can be -1, 0, or +1, okay? The only allowed transitions between these two levels are those that fulfill that the difference between the two M values is 0 or ±1, okay? So in this simple case, which is a Zeeman triplet, you can have a transition from the lower level to the upper level from 0 to -1. You can have a transition from 0 to 0 or from 0 to +1, okay? And this would directly correspond to the red component, to the central component, or the P component, and to the blue component, okay? These are the ones that we could explain using just the classical physics, okay? The number of magnetic levels, of course, depends on the J quantum number. So you can have two J plus 1 different two levels when you have the presence of a magnetic field. So if J is equal to, you will have just 5 different magnetic sublevels, okay? So depending on the transitions, you may have many components or just 3, okay, or none, okay? Because if you have a transition from G equals 0 to G equals 0, you only can have one transition, actually, okay? Actually, that transition is not allowed anyway, but well, this would be the case when you have a transition between J equal 1 and J equal 2, okay? Here in this case, you have the splitting of the magnetic sublevels in 3 different sublevels, -1, 0, and +1. This one can split in many more, so from -2 to +2 in 5 different levels, okay? And then you can look for the allowed transitions here, okay? And then you will realize that only these 3 are the ones that change from -1 to -2, from -1 to -1 to from -1 to 0 are the only ones that fulfill the condition, and also for the central component and the blue component, okay? So you cannot have as many transitions as you want. You have to just fulfill the rules for the quantum mechanics, okay? So in this case, the components of the magnetic field will be many more than 3, okay? So you can see here, sorry, that the splitting, okay, in wavelength is now given by these quantum numbers, M quantum numbers, and also by these 2 values, which is the factors of each of the transitions, which actually are calculated directly from the quantum numbers of the level. Okay, so I don't have here the expression of the Landé factors, but you can find them in the books. Okay, and every level has its own Landé factor. Okay, depending on the quantum numbers. Okay, so and then now in the equations for phi sub that you have here before, let me go back. well, this one doesn't matter. So each of these profiles, which is P, B, and R, are related with the P central component, sigma, blue, and red components, okay? But it's just not a single absorption profile or dispersion profile, but it's composed of many of them, okay? Depending on how many transitions do you have for the red, for the blue, and for the principal component, okay? And it actually basically depends on the quantum state of the atom, okay? So I have a slide here about in the real case, how it looks like, this effect. This is actually a real result from the the spacecraft. I don't know if you know this instrument, but this is interesting because it has two different spectral lines, which is iron 6301 and 6302, and these two lines, one of them is anomalous Zeeman, and the other one is a pure triplet, okay? And when you go through the sunspot umbra, okay, where you have the magnetic field pointing towards the observer, remember, the radiative transfer equation is telling you that in that situation, Q and U is not there. You have only an equation for I and V. Is the only two equations that are coupled. The other ones are just zero because there is no source function. You can see actually how the Stokes V here splits, okay, a lot. Okay, and these are the red and blue components, okay, of the splitting in both lines. Okay, in this case, I wanted to see this graph because I thought there was no linear polarization actually in the umbra, but there is some linear polarization. But in principle, if the field is completely aligned with the line of sight, you won't see linear polarization here, okay? You will see a lot of linear polarization in the penumbra, where the field is perpendicular, okay? And as I was explaining you only have I or Q, or a combination of Q and U, depending on the azimuth value, okay? And no Stokes V. In reality, you have all of them, okay? But these two lines differ in the splitting. One of them is a normal Zeeman effect, and the other one is an anomalous Zeeman effect, okay? And in reality, when you go to the profiles, you don't see any difference. So you don't realize that one has few three components and the other one has many. Actually, from this plot, you cannot identify them. Okay, it's very difficult to identify them. You have to know it because you know the configuration. Okay, but what I can tell you is that you can, for instance, assume that both of them are triplets, simple triplets, and then you can try to reproduce the profiles, and you will see that you are unable to reproduce one of them because you just missed the different components, the many components that they have, okay? This is also important to see that the splitting is perfectly seen in the intensity, okay? And this is because Stokes I is also sees the magnetic field, okay? And actually Stokes I, when the magnetic field is strong, can be actually used for diagnosing the magnetic field strength directly, because what you see there is the splitting. And here is, I like this plot because here you can see that you have a central component and two blue and red and blue components, okay? And the field is so strong that you clearly see the splitting of the line in Stokes I, okay? And from this measurement, that's you can directly say that the field strength here was really strong, okay? By the way, this one is a pure Zeeman triplet. This is the second one, and the first one is an anomalous Zeeman effect, okay? But in this one is really nice to see. Okay, you don't need to do any radiative transfer. You don't need to solve any equation. You just go to the profile, look at it, take your ruler and measure the splitting. Okay. In any other situation, it's much more difficult than that because usually the splitting is not very well seen in the spectral lines, only when the sunspot has an umbra which is strong enough, okay? And then you have really to use inversion codes and things like that, okay? This is also important to see that these spectral lines, they actually sense the magnetic field as well. Many people, I don't know why they so believe that Stokes I is insensitive to the magnetic field in the solar atmosphere, and this is not the case. Stokes I is also sensitive to the magnetic field. Okay, we can discuss whether if it is very sensitive or not when the magnetic field is very weak, but it is sensitive. So when you want to determine the magnetic field strength in the solar atmosphere, you have to include the 4 Stokes parameters. Okay, you cannot do with the 3 describing polarization, Q, U, and V alone. You need to include the Stokes I. Okay. Well, when you write down the radiative transfer equation, taking into account the fact that you can split the magnetic field, the lines in different levels, you have to change basically to write down the new equation, and you have to take into account the different Zeeman splittings for the different components, okay, either in frequency or in wavelength, and then write down the absorption and dispersion profiles, including the splitting, okay, and in this new absorption and dispersion profiles, you now realize that there is a new term here, okay, which is the sum of these S values, and this is because every transition contributing to the splitting, okay, has its own strength. I mean, they contribute differently, and you have to take that into account, okay? You can arrive to practical equations, how to calculate these values and put it in your model. This comes from quantum mechanics, basically, but you have to take into account that when you have more than one allowed transition, like here, you have 3, you have to weight each of them, okay? And each of them, and then separately. So you weight the red, the central, and the blue component separately. Okay, so when you find out that you have also this additional term, is because you have to take that into account. Okay. And well, this is an example as well, but this, in this case, there is no Stokes profiles. It's just the propagation matrix element, and here you can really see. Not in the data is much more difficult to see because the lines are usually broader because of thermal broadening. But here you can tweak the parameters and put smaller thermal broadening just to see how the splitting works. And here you have 2 different transitions. For instance, you have this transition. Remember the spectroscopic notation, okay? So you have this J thing, which is 2 and 1, and then it will tell you how many transitions are allowed, actually. Here you have another different transition between 2 different levels with 2 different J values and so on. And you will see from this plot, actually, you can really see which one is a triplet and which one is not really a triplet, okay? When you have a triplet, the combination of the absorption and dispersion profiles actually is just a Gaussian and a Stokes B shape-like profile, and the combination of them in the propagation matrix is the one that gives you these different shapes for 2 different magnetic field strengths. You can see that they are simpler profiles, not that complicated profiles. This is a triplet, actually. When you have a multiplet, the combination of the profiles really change the shape of the different elements in the propagation matrix, okay? So you can see how you have different lobes and different contributions. So the shapes are different, rather different. Actually, this is regarding the Zeeman effect in most of the spectral lines in the solar atmosphere. You can have much more complex pattern, okay? There are spectral lines that are also sensitive to the hyperfine structure, for instance. And then when you see those lines, the splitting of the different levels is much more difficult, no? It's actually not symmetric, it can be in many ways and so on. And when you look at observations on those lines, you don't see anymore as normal Stokes P or Stokes Q profile. You see different shapes, okay? But most of the lines can really be analyzed just using the Zeeman effect, fortunately. Well, and this is just a summary, okay, of the radiative transfer equation in the presence of a magnetic field, okay? So before the summary, I don't know if you have any questions regarding how about what we have been talking so far. There is a question actually there.
To go back to the previous slide, I noticed that the transition on the left might be, I don't know if it's really an intercombination line because the spin quantum number is changed from 1 to 2, right?
Yes.
Do we usually use those lines for magnetic field diagnostics?
Well, I have to, I usually don't pay attention to that because we use very few lines, very few lines for diagnosing the magnetic field. I don't know if some of them have different spin, you know, hang. Yeah. Yeah. Yeah, this is not allowed. Yeah, yes, that's true. Yes. Yeah, that's it. Yes. Yeah, these arbitrary examples actually. Just
Okay, thank you. Okay, thank you.
actually, it's very interesting because I usually don't pay attention to the transitions unless you are doing something special with the spectral line. So we have been most of the lines in the photosphere, you know, they are normal Zeeman triplets or multiplets, but in practice, what we have is just a code that takes that into account, and you just put the transition, and we never pay attention on that. I know that, for instance, the SDO spectral line is a pure triplet, okay? The solar orbital line is a pure triplet. The famous 6302 line is triplet as well, and few of them are multiplets. The calcium, the chromospheric lines, they are usually multiplets, isn't it? It's not triplets, but I never pay attention to that. Only when you deal with things like scattering polarization, for instance, you have to be very careful because things change there a lot. So you have to really know what are you doing, because depending on the transition, you can have polarization in the lower level, in the upper level. Well, these things will be discussed, I think, next week, okay, more in detail. But it's only there when we really, in practice, pay attention to the configuration, to the electronic configuration, and so on. yeah, we are so used to have a code that takes care about all these things. Even for the JJ coupling, we can just say this JJ coupling, boom, and you don't care about that, okay? So, but at least you need to know how it is done internally, okay? And this is actually how it is done. It's actually you use quantum mechanics to derive all these things, okay? It is also important to say that, well, the Zeeman regime is one of them. I think Han probably will talk about the other regimes that we have, because the Zeeman, this is only applicable to the Zeeman regime, but we also have the Handler regime, and also the Paschen-Bach regime, and things like that. Okay, so how the spectral line behaves in the presence of a magnetic field, it can be really different depending on the spectral line. Okay, and if some of you are working, I think some of you probably are working with this helium 1030 line, it's not enough to have into account the Zeeman effect. You have to take into account the Paschen-Bach effect. Okay, because the energy levels are very close, and they cross and they interact between them. So you have to take that into account. And when we do those calculations, we don't just do it analytically. We actually solve the Paschen-Bach. We solve the Hamiltonian for the Paschen-Bach effect, which is just something that you do numerically. In the Zeeman effect, you can have it analytically, actually, and we do have it, but not in the Paschen-Bach regime. And well, on Handler, yeah, Handler is next level of understanding. But this important to keep in mind that not all lines are really easy to understand how they behave when you have a magnetic field in the solar atmosphere. Okay. Well, this is the summary of the radiative transfer equation in the presence of a magnetic field. Okay. Well, the radiative transfer equation in local thermodynamic equilibrium and in the presence of a magnetic field, we will always consider, okay, in this case, that the continuum radiation is unpolarized. So, and that the medium is isotropic for the continuum formation and so on. This good. So the continuum radiation should be unpolarized because measuring the polarization in the continuum is really hard. Okay. I don't know if you know which is, a place where the continuum is not unpolarized, and where you have to take into account that it is actually polarized. So I don't know if you know which is the first scenario that you have in the sun where you have to take into account that. So probably you don't know, but if you go to the corona, the continuum in the corona is polarized. Actually, it's polarized a lot because you have the Thomson scattering. It's the continuum of the corona. Okay, so when you look at the corona and you look at the spectral line in the corona, I think the continuum is actually more than half polarized. Okay, and you measure the corona actually with a linear polarizer in a coronagraph. Okay, because you have to separate what is the corona from the rest. Okay, which is anything coming from the atmosphere or anything coming from the cold F corona, which is scattering in the dust on the interplanetary space and so on. So this there we cannot assume that the continuum is unpolarized. We can do so because we do relative measurements at the end, but you have to be careful there. Okay, so we also consider that thermal motions are Maxwellian. Okay, so I don't know anyone resolving the radiative transfer, or if there is any impact in anywhere where thermal motion departs from Maxwellian distributions. I probably Han knows a little bit about that, but usually it's not the case. Okay. In flares, yeah, that's true. In flares, in solar flares, the thermal motions are really not Maxwellian. Okay, so I don't know. Well, this is something I have seen profiles generated in flares, but I don't know anyone talking about spectral lines or polarization signals departing from the RT or somehow because of not much linear velocities. I'm not aware of that, but probably there is an impact. Yeah. Well, yeah, yes, sure. Yes. Okay. Yeah, but this is okay. But I mean, this is really the most basic building blocks, okay, for the radiative transfer in local thermodynamic equilibrium. So there are also other properties like we assume that the system, the atmosphere is plane parallel. Okay, this is very important. We always assume that it's plane parallel and there is no transfer, horizontal transfer, and things like that. We also assume that there is no changes in the material properties in the solar atmosphere. So, for instance, the refraction index is constant. There is no effect from there. That's not a good approximation for other stars. White dwarfs, you have to take that into account. And maybe even in the sun, you have some effects, but nobody have checked that before, as far as I know. And then the other question is that in LTE, and in this case, the absorption, dispersion, and emission is independent of the Stokes vector. Okay, this is not the case in non-LTE. Okay, in the case of non-LTE, you have to take into account that thing. Okay. Also important when you talk about the RTE in local thermodynamic equilibrium is that the radiation field is independent of time. Okay, so we assume that this is in stationary, basically. Okay. You will see, so it is not the case actually in the chromosphere. You have that may have an impact, strong impact in the spectral lines actually, okay? But it is something that is not easy to take into account so far. Well, this is the effect of the refracting index gradient is negligible. Also, we said that the properties of the matter is governed by the thermodynamic equilibrium equations, basically, the Saha and Boltzmann equations, okay? We also assume complete redistribution, so there is no trade-off between different frequencies, okay? So this is something that can happen in LTE, and probably Han will explain next week about that. We also assume that when we have the Zeeman effect, or at single triplet or many transitions, all the levels are equally populated, okay? So there is no imbalance between the different populations. When you have an imbalance between the different populations of the different levels, you have to include Handler, okay? And actually, atomic polarization, okay? This is not the case. We haven't included all these things. For that, you need really to take into account other things. And with all these assumptions, what we have is this equation for the radiative transfer equation in terms of the optical depth in the continuum with the propagation matrix elements, with the Stokes profiles, IQUV, which is represented by the I vector here, with the source functions that in LT, remember, is given by the Planck function, okay? Well, everything in the system, all the thermodynamic, the dynamic, the magnetic, and the atomic and the geometric properties are included in the propagation matrix and in the source function, okay? And when solving this equation, you can already explain many of the spectral lines that we see in the solar atmosphere, mostly in the solar photosphere, okay? Because in the solar chromosphere, you start to see things that deviate from local thermodynamic equilibrium, basically because when you go up in the atmosphere, you decouple the system and then radiation becomes important, okay? Well, things that you have to take into account when you study the RTE in practice is that the The optical depth scale is very important concept, okay? Because it just tells you the typical distances when you do the transfers through the atmosphere, okay? When the optical depth is strong, you know that the photons cannot escape because they are continuously absorbed and re-emitted, okay? When it is small, it becomes below 1, you know that the atmosphere is starting to become transparent, okay? You can see those photons already. In the photosphere, when the optical depth is large enough, we find the solar surface, and it's there where we set the Z equals 0, okay? Which is a scale, basically. And then when you go out, the optical depth starts to decrease, okay? This optical depth is directly related with the continuum absorption coefficient, okay? So when you are down in the atmosphere, the optical depth is large because the absorption in the continuum is large. So this scale is actually large. So you have a mean free path for the photons that can be much larger than 100 or 200 kilometers, or even infinite, because it's already opaque, okay? When you go up in the atmosphere, the optical depth decreases, and then the photon mean free path increases, okay? Because photons can travel longer distances without interacting with any matter, basically, okay? So these things always appear in all discussions. And you have to know that this optical depth is directly related with the opacity in the continuum. Usually we need to have a reference, because when you set the opacity at the continuum, you can say, okay, this is my surface, and you say that Z is equal 0 there, but you actually need a reference. When we solve the radiative transfer equation, we write it again with respect the opacity of the continuum at 300 nanometers, okay? 300 nanometers is just that one, doesn't matter. It could be 400 or 600, but it's typically done at 500 nanometers. If you do so, you have a reference where you have, with which you can compare with, okay? So you have one profile in one place, another profile in another place in your map, and you have always the same reference in both of them. So you can really compare optical depths. And even you can even try to compare optical depths in terms of kilometers, but this is very difficult because actually they are independent measurements, okay? Well, also, well, the thermodynamics enters into the equation through the Planck's function and in the propagation matrix. The Planck functions only depends on the local temperature, okay? So this is uniquely determined with the temperature, okay? While the absorption and the elements of the propagation matrix depends on the temperature and the density, okay? Because we are in local thermodynamic equilibrium, and you determine that just using the Boltzmann equations, okay? To see how much of what you have there, okay? Well, and you also have to take into account that all the thermodynamics, all the thermodynamics aspects of the atmosphere are also included there, like the thermal broadening or the microturbulence broadening is also included in the RT, and also you have included the macroscopic velocities, okay, through just the line of sight velocity, which is the easiest thing, okay. Well, other things that you have to take into account is that all the quantum numbers and the oscillator strengths and so on related with particular line transitions are explicitly in the propagation matrix, okay? So once you know the transition you want to analyze, all these quantum numbers go to the absorption and dispersion profiles, and as we have been seeing a while ago. Okay. And also important is that the magnetic field, basically the one that tells you which is the contribution of all the elements in the propagation matrix. Okay. Remember that we have started the definition of the RTE, from an isotropic medium. Okay. And at the end, we have included the source function, the emission term. And all of a sudden, we have said that the medium is isotropic, but we have introduced the anisotropy through the magnetic field. So it's the magnetic field, the one that gave shape to all the different elements in the propagation matrix. Okay, so that's important. Okay, and well, and I think this basically the summary of the radiative transfer equation in the presence of a magnetic field. And what we have to do now is actually to try to solve it in real cases. Okay, try to provide a solution to the equation. This is what we are going to start tomorrow. It's more complicated. Well, it's easy to do, but it's more complicated to understand because there are a lot of concepts that appear in the literature related to the way we solve the radiative transfer equation. And these concepts are things like the contribution functions, the response functions, the height formations of the lines, and how you interpret all these things in reality, starting from the RTE in local thermodynamic equilibrium. Okay, so the next 3 days we will spending a lot of time actually understanding those things. Okay, it's because those are in practice the ones that you use when you want to interpret your observations. Okay, and this is what we were going to discuss. I think we can stop here. I think. No, I don't know the time. It's okay. Is this the right time? Okay. So, do you have any question or something? We have later a question and answer or something.
Check the levels. Great. Well, welcome back, everybody. We're going to be talking here some more now about polarization and the measurement of polarization. So, you know, we, again, thanks to Ivan and Bruce Lights, and also this great book by Jose Carlos del Toro Iniesta. He did this introduction to spectropolarimetry, which is sort of the basis for some of the things we'll be looking at today. Book's available, I think, online as well. Oh, there we are. So where did we leave off yesterday? Lost my mouse. So yesterday we found this this sort of neat way where with a retarder you can convert the circular polarization to linear polarization. So that was neat. Now we have a way to measure, to figure out whether there's circular polarization in our light beam, right? Which is good. You know, the basic idea here is in sort of static form. You have the circular polarization coming in, quarter wave plate, and this linear polarizer the quarter wave plate will convert that circular polarization to linear polarization in one direction. And then you can sort of test for that, the presence of that linear polarization with a linear polarizer oriented in one of, two directions. So that's sort of, a neat, optics trick. But how do we go from that to being able to actually get the Stokes vector, which is what we want, right? How do we actually get through a series of measurements, figure out what that Stokes vector is, the I, Q, U, and V. And to do that, we need we need to do polarization analysis. We need to actually make a series of measurements. And so we're going to first go through, starting back from the electric vector and the electromagnetic wave itself, and figure out how we can do that measurement using a linear polarizer and a retarder. So if I put a linear polarizer in the beam, right, I have both EX and EY coming in here. The linear polarizer will just take the components in those two directions, depending on what the angle is of that linear polarizer. So I'll get out something electric vector at an angle corresponding to that linear polarizer. That's the combination of these two components. If I put a retarder in the beam over here, same thing. I put in this retarder that has a fast axis, so that's where the wave is going through with a lower index of refraction, and then the slow axis is, the one that's doing the axis on which the wave will be retarded with respect to the fast axis. And so in this case, I'm going to line up so that the fast axis is aligned with EX for simplicity here. So I can put my fast axis corresponding to one of the directions of the electric vector, so it doesn't do anything, right? Not that we can observe, so the wave comes through unchanged, but in the Y direction, because of that different propagation speed, I introduce this phase delay. And so now I have both EX and EY, but with a phase delay in the Y direction. Okay, now what if I put those two things in series like we had before? I put that retarder up front, I get my those two components, right, the EX and EY, and then I put it through the linear polarizer. And so now I get the combination of these two. I have my phase delay, and then I have the linear polarizer that takes the component, the sine and the cosine, right, of these two. And so my total final electric vector here is the sum of this of the X and the Y components, right, where I've introduced the phase delay in the Y component. So this is what is coming through this combination that we saw before, a retarder and then a linear polarizer. So how do we get now from that electric vector, those two components of the electric vector, now to our intensities? Well, the intensity, of course, is just going to be the time average, right, of that electric vector and its conjugate. So the intensity I'm going to get out, is depending on, it depends on the angle of my polarizer. It depends on the phase delay I introduce, but it's just the combination of these two. So, I can, multiply this out, do the algebra. I get the two components here, the E theta and the E theta, the conjugate there. And I can, multiply these out. And what I get is these four different components, right? I have my EX and its conjugate, EY and its conjugate, right, on these two. And then I have the two where I'm sort of mixing the EX and the EY with the sine and with the phase delay. So, this is the full description of the electric vector coming out through these two, or the intensity coming out when I sum up those. There's the time integration of that electric vector. Now, if we go back and remember, we had this Jones formalism tensor we talked about yesterday, where we can sort of break down and, we have all the information on the phases, and we can, maintain that information with the Jones tensor. And this has these same four components, right? Where I have the different combinations of the electric field components in the two directions and their conjugates. And remember, these could be written because they were the time average just as the two amplitudes, AX and AY, and then the combination of the two amplitudes and the phase difference. So, you know, I can relate the time average here of this electric vector to the it just gives me the amplitude of these things. And we also remember the Stokes parameters were defined as the sum, right, of these of the AX and the AY, or the difference in the case of the Q, or right, they were taken from these two diagonal terms, the sum and the difference in diagonal terms, and the same, the UV was the sort of the sum and the difference of these two diagonal terms. So now I can relate my Stokes parameters back to you know, the electric vector, the electromagnetic wave itself. So now I can take this, you know, write out this whole combination here. For example, EX and its conjugate is just AX squared, but AX squared I can relate back through the Stokes parameters and calculate this out, and I find out AX squared is just I plus Q, right? If I just add I plus Q, I just get AX squared, I divide by 2. And so now I know that this complex, this time average of the electric vector here is just I plus Q, right? That's what we had sort of found before. Same thing, I can do this for all 4 of these different components, and I see that each one is a different combination of I and Q or U and V. So now I have a way to relate my these different components of the electric vector back to the Stokes parameters themselves. So that's good. So how do we get from there to our measurements? Well, we had this equation we had figured out before, that the entire intensity coming out through this combination of the retarder and the polarizer was this big long thing here, right? But then now I can take these different combinations of the EX and EY and substitute back in my Stokes components here, right? My I plus Q, I minus Q, and the U and V combinations here, right? And so now, instead of expressing it just as the 2 different electric field components, I now can express these as Stokes components. And adding this up, summing these different things up, multiplying them out, you find out that this intensity that you get out is just the sum of IQ, U, and V, right? There's 4 different components to this in my output intensity, and it contains all of these IQ, U, and V, the different Stokes components, multiplied by, you know, different, depending on the angle of the polarizer and the amount of phase delay I introduce into the beam, you know, I get a different intensity out, but I can see that this intensity contains all 4 Stokes components in it. So that's good. Now I've been able to, I know how to express this beam, this electromagnetic wave coming through this retarder and polarizer now as my Stokes components. So now, but that's one measurement, right? That's my total intensity coming out. Now we want to figure out how to sort of separate those out and figure out, you know, how to isolate IQ, U, and V and measure each of those independently. Well, right, IQ, U, and V, this thing here depends on the angle of the polarizer and the amount of phase delay I introduce, right? So what happens if I play with those numbers, right? Try different angles of the polarizer and or different phase delays. You know, can I isolate different components here of the Stokes vector? So if I start and say, okay, let's put it at 0 degrees, right? That's what we did yesterday in our thought experiment. We just, you know, put the polarizer vertically. So if it's 0 degrees, right, theta, then these, the 2 sine components here drop out completely, and I just have I plus Q, right? So that's good. Now I've got I plus Q. I've eliminated 2 components with that by just putting that one polarizer measurement, and I just have the sum of 2 Stokes components. Now I rotate my polarizer 90 degrees, right? And now I get the opposite sign from that cosine term, and I get I minus Q. So now I've got I plus Q and I minus Q, and it's easy enough to look to see that I can just add or subtract those two measurements, and now I have a measurement directly of I or a measurement directly of Q, right? So by combining these two, I can measure I and Q and have those and determine what those are, what those components of the Stokes vector are. I can do the same thing now. Instead of 90 degrees, 0 and 90, I use that 45-degree angle, and I can separate out, I eliminate the V and the Q components, and I just get I plus or minus U, right? And then so I can express U now as the sum of these two different measurements. Or actually the difference of those two different measurements. Yep, it should be a minus sign there. So that is, now I can get I, Q, and U just by different measurements with the polarizer, right? This is kind of what we saw again yesterday when we were thinking about it. If, I can measure with these polarizer at 0, 45, and 90 and get, most of the information about the linear polarization of my light beam. So this is good. I have I, Q, and U isolated. How do I get V? Well, there's no, I can't do that just by rotating the linear polarizer. There's no way to set two angles that will allow me to isolate just Stokes V here. So I'm going to need to do something with introducing a phase delay, right? Using the value of delta here and what phase delay I introduce into the beam. And so if I introduce a 90-degree phase delay, a quarter wave, right? Then in this case, now I eliminate the Q and U terms, and I get I plus V and I minus V. And now I can get V just by taking the difference of those two. So by these series of just a series of measurements now, right? Just by setting my polarizer at 4 different angles and introducing a phase delay for 2 measurements, a retardance for 2 measurements, I can get the entire Stokes vectors. So now we know exactly how you would go about with a polarizer and a quarter wave retarder to be able to, fully measure the Stokes vector for an incoming light beam. So that's pretty good. We can actually finally measure this Stokes vector. So, one thing we see here is there's this connection between Q and V, or between U and V. And, that's just because, as we saw, this linear polarization, the quarter wave plate is changing linear polarization to circular polarization or back and forth. So that's why there's this sort of, those two are connected in our measurement scheme. They're both affected by that phase delay. So here are the measurements we would need, right? To get IQ and U and V, we would need these measurements, 2 of them, right? These are the same. So we don't need, that's just a single, these 2 are the same repeated measurements. So for 6 measurements, with 6 measurements, I can get the Stokes vector, right? Just by combining them in the proper way. And if we look at this goes back to what we were seeing yesterday, right? If I put in my polarizer at 0 degrees, I'm measuring just getting the linear polarization. Then I put it in at 90 degrees, right? And I'm measuring the horizontal polarization. So this is I is the sum of those 2, Q is the difference. Again, we have our 45 and 135 degree orientation of our polarizer. We take the difference of those 2, and we get the U, sign conventions. And then the V is just the difference, again, of these 2 circular polarization measurements, right? This is converting the circular polarization into this 45-degree linear polarization, and this is converting circular polarization into the 135 degrees. So I just take the difference of those 2, and that's just taking the difference of the 2 circular polarization states. So, this really explains how, going from the electric field, the electromagnetic vector, we get directly to the Stokes, sort of the Stokes measurement of the Stokes states. So, and it just defines, shows how closely that Stokes formalism is sort of connected back to the inherent properties of the wave itself, right? It's not, it's closely coupled with the underlying physics. And so go back, we're talking about Stokes vectors. Well, just remind ourselves what the 6 different Stokes components, or the 6 different Stokes vectors we can think of, right? We have plus Q and minus Q, so the 2 polarization states, 0 and 90. Here we have 45 and 135, and then the 2 different circular polarization states. So, these are sort of the Stokes vectors, the fundamental ones. But what we've seen now is we can sort of think about, well, I can start with this right circular polarization Stokes vector, and I can put this thing in the middle and I convert it to another Stokes vector, right? Or I can do it in the opposite direction, right? I can start with my 45-degree linear polarization, put in a quarter wave plate, and I get circular polarization out. So there's some sort of mapping between these Stokes vectors, right? I can do the same thing. I can put in a linear polarizer, and so I'll knock out, if I have Q and U, I can, completely get rid of that one component of the polarization, and I'll have it in just one component of the linear polarization, just the Q. I can take my unpolarized light, and through some processes, scattering or something, I can generate linear polarization, for example. So how do we think about this kind of mapping where I can go, I have one Stokes vector and now it turns into another Stokes vector? Because, this process here, where I'm using this quarter wave plate, this retarder, to convert between Stokes vectors, is really fundamental to our measurements. And so we want to sort of think about how we can describe that and use that to, plan our measurements. So the way we do that is through the Mueller matrix, or Mueller matrices, which allow us to go from a Stokes vector, right? This is using matrix algebra here. I can devise a Mueller matrix of, 4x4 Mueller matrix that I can multiply by a Stokes vector, and I should be able to get out another Stokes vector. I get these by, but the math here is, the process is I take all my components in one row, multiply them by my Stokes vector, and then this gives me, in this case, since I'm doing the 3rd row, this will give me the U prime output. So it's the sum of the Mueller matrix elements times each of the Stokes components, and that will give me, a new linear polarization, this 45-degree linear polarization, the U component here. And, this can be, arbitrarily, complex matrix, so to speak. There are some, rules to it, because I am trying to, construct a valid, take a input Stokes vector and construct a valid output Stokes vector. Another way to think of this is by, each of these 16 components sort of is a mapping from one Stokes component into another, right? So, on the diagonal, I have the I to I, Q to Q, U to U, and V to V. So that, if I have a Euler matrix, it's just a diagonal with ones, then I just will get the same vector out that I put in. But in the other cases, there's, this is where I would see, for example, I can see, unpolarized light going into polarized light through this, or the conversion of different linear polarization components. For example, we were talking about what we were showing was that with the circular polarizer, we can go from the Stokes V to the Stokes Q. We convert the circular to the linear polarization. Well, that's right here, right? So here I'm converting circular polarization into linear polarization. And here we're going the opposite direction, linear into circular. So we'll see that when we look at some specific Mueller matrices, you'll see these two components are sort of where we're capturing that mapping that the retarder is converting those to. And then up here, we also see where Q and I are mapped together, or I to U are mapped together. So as I said, these matrices can do a lot of things. It's all through matrix multiplication. They can rotate. I can rotate the coordinates of my polarization if I'm measuring it at a certain orientation. Through matrix multiplication, I can just apply a rotation to my coordinate system. That's one use for the Mueller matrices, right? If I have this angle, I can capture that here and apply that rotation to my incoming Stokes vector. One thing you'll notice here is this rotation has this factor of 2 in here. And in part, that factor of 2 is tied back to the fact we've been talking about linear polarization, right? It's measuring from 0 to 180, basically. We don't have the whole wave period is captured in just 180 degrees of rotation. So this is sort of turns out to be very fundamental in when we're measuring magnetic fields, that we aren't measuring, we don't get the full 360 degrees. We have an ambiguity in that we don't know exactly the direction of the polarizer. And so we have an ambiguity in whether the orientation is, an angle or that angle plus 180. And so that turns out to be, when we're measuring magnetic fields on the sun, we have this ambiguity in which direction the vector is actually pointing. That turns out to be a tricky problem and hard to solve. And it just goes back to the fundamental nature of of polarization, how we measure it. The other way of thinking about the Mueller matrices is that they're just a remapping onto this Poincaré sphere that we talked about. Davide talked about, and I mentioned yesterday that, right, we have this sphere and any sort of Stokes vector sort of where of totally polarized light is sort of a unit vector that, somewhere on the sphere, partially polarized light that, it's a unit, it's a vector, but doesn't get to the surface of the sphere. But what the Mueller matrices are doing is basically remapping my vector on that Poincaré sphere, right? And the easiest one here, again, we'll go back to it, is, I have right circular polarization. I use that quarter wave retarder. I apply that Mueller matrices, and now it rotates, right, my vector down into here where it's, linear polarization in one direction. And I can do the same thing, right, and then apply that matrices in the opposite direction, and it rotates me back around. So the Mueller matrices is just sort of changing, can reorient the vector in this sort of 3D space. So sometimes, that's another way of thinking about what's going on and visualizing the effect of these different Mueller matrices. So as I said, let's look at some, we talked about linear polarizers, retarders. What do the Mueller matrices for those specific optical elements look like? So if we have a linear polarizer at 0 degrees, right, then my Mueller matrix in that case turns out to be just up here with I and Q, right, since that's the only part that's involved when I have that linear polarizer. And so if I put in, light that's already polarized, pure Q, right, I would just get out pure Q again, right? I put in the polarizer, I apply that Mueller matrices, nothing happens because all the light goes through. If I put in negative Q, right, so now it's all perpendicularly polarized light, and I apply this Mueller matrices, you can, calculate this out, and it turns out all the light disappears, right, as we expect, right? The sum and the difference of these, zeroes that out. So as we, you cross the polarizers basically, and you've attenuated all the light. If I put in unpolarized light, right, now, right, I have no Q, U, and V, just unpolarized light, and I go through here. Now I see I get half of the intensity of that beam out, right? I have this half up front, so when I multiply this out, I've cut the total intensity of the beam in half, and the only light that remains is in that Q, that vertical polarization state. So, you sort of see how these things, they do what we expect, right? I mean, this is sort of, we know this is what happens if I cross the polarizers, it goes to zero, but we see that this Mueller matrix is capturing that, and how that sort of carries through. So yeah, this is just, how you would add this up, right? I'm just adding up Q and U. And so, that's how it's calculating these out. In all cases, U and V coming out, U prime and V prime, because I have, right, these are all zero in the down here. There will be going through a linear polarizer, no circuit, no polarization is going to come through that polarizer. If I rotate that polarizer by 90 degrees, now I get -1s in this diagonal here. And, now putting in pure Q, I get nothing out, but if I have negative Q, I get, it properly propagates through that horizontally oriented polarizer. And the same thing now, I put in totally unpolarized light, I get half the intensity out, but oriented in the opposite direction. Well, that's good. But if we have something a little more complex, we can take our linear polarizer, and instead of having 0 or 90, the basic calculation is this, right? This is the full description of a linear polarizer at an arbitrary angle, right? And it's got a lot of different components here, but you see why if it was 0 degrees, I only get these 4 components. If it's 90 degrees, I only get these 4 here, right? And these were the ones where I had Q to I and Q to Q. These were I to U and U to U. So that's why these are the only ones that persist if I have, if I'm exactly at that angle. And if I have some intermediate angle, I'll start mixing Q to U and U to Q in these 2 components, right? So, you can see how this sort of carries through the combines different polarization states, doesn't do anything to the circular polarization. That I can, change by putting in a retarder instead, right? And now I can see what the Mueller matrix is for a retarder with some phase delay of delta. And now we see it operates down here in this lower part of the Mueller matrix. Again, coupling, as we'd seen, coupling that the U and the V, right? Because of the way that this retarder is working, converting linear to circular and vice versa. So these are my sort of components here, but it won't do anything. The retarder doesn't do anything if I send in purely linear polarized light at 45 degrees to that fast axis of the retarder. So the Q will always just come through. And so, I can try different combinations here where I put in some U and V polarization, and I can, get out these different components. If it's, I think that's like for a 90 degree, it will map one to the other and vice versa, right? If I give it both U and V at the same time, it'll convert one to circular and the other one back to linear. So, and this is an example of that, the Mueller matrix, if I have the delta is 90, right? So now I get -1 here. So then I'm converting my circular polarization to negative U, and I convert my U now is converted directly into V. So that's what's shown over here. So that's good. Again, we can express this. There's a generic description of what the Mueller matrix is for a arbitrary retarder with a arbitrary phase delay delta and an arbitrary angle of the fast axis with respect to my the Q and U axes. And it's gets a little messier trying to combine all these things, but again, it's a fairly straightforward matrix. So now I have these Mueller matrix. I know what the Mueller matrix is for a linear polarizer. I know what it is for a retarder. And I can just combine these things, right? I can do linear combinations of these Mueller matrices, just doing my matrix algebra, and calculate what this final output is going to be. So my input intensity coming in is the I, Stokes I here. I have the Mueller matrix for my retarder, and then my polarizer, and then this is what the intensity I should get out. See, it goes, in the direction or the opposite direction of the propagation of the light here. So this is the Mueller matrix, right, for a polarizer oriented at 90 degrees, or at, sorry, 45 degrees, right? I have these 4 components here, or the 3 here, where it's affecting U. And so that's what my polarizer is. And then I have my retarder over here, right? It doesn't affect Q, but it does this, has these 2 components on this, here on the diagonal converting between U and V, right? So now I have these 2, I can multiply these out, right? And I can do this, I switch my circular polarizer, right? Sorry, my retarder switches V and U, right, down here. And then I put it through the linear polarizer, which, extinguishes the Q. And I can, calculate this out, and I get I minus V is my intensity coming out, which is what we saw before, right? I put these 2 things in series with the retarder and that polarizer at 45 degrees. I just get I minus V. And that is what the same thing, what the Mueller matrices are allowing us to do now, with simple, matrix calculations. So this is a really powerful way to sort of think about the polarization and what your optical system is doing to it. It can capture any translation between the different Stokes states going in to what's coming out. So that's very, very useful to be able to describe your system in this way. And the fact you can sort of combine these Euler matrices and, just multiply them out as I go through an optical system allows me to sort of calculate, piecewise what the effect is of the different optics are in my optical system. So, that's a really, important way we do in order to sort of figure out the polarization of our entire optical system. Are there any questions at this point? Okay. So we'll go on and look now at some sort of some other cases here where we can use these Mueller matrices now to think about measurements more in detail. We saw this going back here, right? This was my measurement going through the retarder and the linear polarizer, and my 6 sort of measurements I would need to make to characterize the light. And, this is how we think about the Stokes vector here. But now we can think about this and write it out as a series of Mueller matrices that are applied to my measurement for each one of these, right? For 0, 0, this is the Mueller matrix, right? That's applied. For the 90, now it's the same thing. I have -1 on these diagonals here. The 45 and 135 and these 2 Mueller matrices. And then this is the 2 circular polarization matrices. I think I got that right. Yeah, because I have these include the 45-degree linear polarizer in there. So I have these, 6 Mueller matrices. Now it turns out when you're sort of calculating what you want to see at the end, right? When I'm going to actually measure, only depends on the top row of that Mueller matrix when I'm finally determining what my output intensity is, right? Because this is the one that, this row against the Stokes vector gives me I, and all I measure in the end is I, is the total intensity through that system, right? I'm not actually measuring the Q, U, and V, I'm just measuring the total intensity and combining that. So, these are the key things here when I want to figure out, the total effect when I combine all my Mueller matrices into one, right, what is the final effect? And so the important one when we're sort of figuring out doing these series of measurements is this top row here. And I can combine these 6 and pull them all out and stack them up. And this is what we call our modulation matrix. So modulation is what we're doing here, right? We're sort of by changing the optical components in the beam, we're changing the intensity, the final intensity coming out on our detector. And so, we're modulating the intensity, and this modulation matrix is a way to think about, okay, here's the series of the 6 measurements I'm doing, or the intensities coming out from my 6 measurements, right? And if you think about it, you can read this off, right? It's almost I plus Q, I minus Q, I plus U, I minus U, I plus V, and I minus V, right? That was the 6 measurements we were doing, and that's sort of captured here in this modulation matrix. And so it sort of explains, compact form, what the different measurements we're doing are. And so this is a way to describe, different modulation schemes. So why is there more than one scheme, right? I mean, I have the way to measure, the Stokes vector. Why would I do it any other way? Well, there's, a variety of reasons why, you wouldn't always use these exact 6 measurements to measure your Stokes vector. Some of those are, sort of instrumental, and some are, based on questions of efficiency in terms of measuring, these 4 components in the most information-rich manner. One thing you'll notice is I'm measuring 4 things, but with 6 different measurements. So somehow there implies there's an inherent inefficiency in that somehow, right? I should be able to take 4 measurements and get 4 values out. And you could, right? I could take, I plus or minus Q, right? And that would give me a value for I, would give me a value for Q. And then I could just take one measurement of I plus U, I minus U, and subtract off my I measurement. And, that would give me my, my U and V directly without having to measure plus or minus. There's a few problems with that. One is that, there's inherent sort of, that makes it very dependent on errors in I, which tends to be much larger than your Stokes signal. So if I get my I a little bit wrong in my measurement, it's no longer a differential measurement, but now I need to have my absolute measurement of I be very precise with respect to this, measurement of Q and U that could be, 3-4 orders of magnitude smaller. The other is that if I do it like that, I'm taking 2 Q measurements, but only 1 U and V measurement. So somehow I'm getting 2 measurements of one Stokes state. So I'm getting that with more precisely, right? I'm getting a better signal in my Q than I am in my U and V. And so now I'm sort of imbalanced, and I'm more sensitive to Q in that case than I am to the other Stokes measurements. So there's, reasons why that's not good, to sample one Stokes parameter more than the other. So, if we want to get away from that, how can we modulate, right? What are our actual, ways we modulate at the telescope? Here I was talking about I put in a polarizer at 0, and then I rotate it to 90, and then 45 and 135. And then I put in this retarder and take it out. Practically that's a harder, can be a hard thing to do, moving these optical components in and out of the beam or rotating them. So sometimes it's easier if I can just put 2 components in the beam, right? And change them through electrical means, perhaps. Yesterday, we talked about these liquid crystal variable retarders. I just apply a voltage and I can change the retardance. So, that's nice. I can put 2 of those in the beam. And as we'll see, that allows me to make a series of measurements of the Stokes vector with nothing moving, right? Which is good, because anytime you start moving things in an optical beam and you have questions of alignment and all sorts of small little details come in that make your life much worse. So having 2 components that just sit in the beam in a fixed orientation is good. And then, what we'll see is they'll output, information, and I can put in a fixed linear polarizer, which will allow me to sort of sample out one of those polarization orientations to analyze the beam, and that will go to my detector. Turns out in practice, we often don't use a single fixed linear polarizer because I'm getting what comes through these two liquid crystals is the two different orientations, two different orthogonal polarizations. If I just put in a linear polarizer, then I'm sort of throwing away half the light. And, we hate to throw away light. So we often put in a polarizing beam splitter, and then we send these two beams, the two orientations of the polarization to our detector, or to two different detectors. So what we're doing now is we're changing the retardances of liquid crystal 1 and 2 in time. So we call this a temporal modulation. There's ways to do this sort of spatially, but in this case, because we're changing in time, it's a different modulation type. So we can go back to our Mueller matrices and figure out what we want to do here. I have my light coming in. I have these two liquid crystals, a polarizer, and then my detector. So I can have three different Mueller matrices that I multiply up and figure out what my emergent intensity is. And so my liquid crystals here, depending on, they each have a fast axis and a slow axis. What's useful is if I take the first liquid crystal in one orientation, and then I rotate the second one at a 45 degrees orientation, the fast axis rotated 45 degrees with respect to the first one. Because what that does for me here, right, if it's just a simple retarder, right, it just operates on Q and U, that first liquid crystal, or sorry, on U and V, right? It does what we saw before, simple retarder oriented to the axis, just has components, just operates on U and V down here as I change the retardants. But if I rotate it by 45 degrees and I go back to that big complicated matrix of where I had an arbitrary phases, phase delays and angle, I can calculate it out, and I find now this retarder also operates on on Q up here, right? And so now I have a way by combining these to both modulate my U and my V, but also my Q, and be able to measure all three by changing the retardants, combinations of the different retardances on these two liquid crystals. So I have the delta 1 is my retardance on liquid crystal 1. I can put a different retardance, delta 2, on my liquid crystal 2. And I can combine these two Mueller matrices, right? Multiply them out. And I get this sort of combination here, where in this case, my IQ, U, and V, I have just the retardance on liquid crystal 2, since liquid crystal 1 doesn't do anything, right, to my Q signal. And then I have these combinations here in the U and the V of both my retardants on both on liquid crystal 1 and liquid crystal 2, right? So this is good. Now I have ways to sort of change the retardants and sample the three different components of my Stokes vector. You'll see this, then there's, the polarizing beam splitter just has this plus and minus, which indicates I'm taking both. I'm not just using a simple linear polarizer, in which case it would just be a 1 or, just be a 1 or -1, because I'm, hypothesizing I'm using a polarizing beam splitter that is able to sample both of those two orthogonal states. I get both the plus or minus component depending on which beam I'm measuring, beam I'm measuring coming off of that polarizing beam splitter. What you see is all the light is in the 0 and the 90-degree polarization, which is why, I want that polarizing beam splitter will be able to sample either the 0 or the 90 completely. So how do we, what values do we set? This is great. I have these angles here. I can then calculate what values I want to set for the those two different retardances in a series of measurements in order to, to be able to measure independently Q, U, and V. And so I can go through and through a series again of 6 measurements, right? By, with 0 retardants or half wave retardants, I can get plus or minus Q. I have combinations of quarter wave retardants here and a quarter or 3/4 wave retardants here, I get U. And then if I just modulate the liquid crystal 2, I get plus or minus V. So by these, combinations, and you can sort of show this again, that I'm able to sample I, Q, U, and V completely with these 6 measurements just by changing the retardants on these 2 liquid crystals. So, that's nice. You see 0 here. Now, that's not a true 0, as we'll see, because as we saw, there's always some latent retardants in these, anytime I'm going through these liquid crystals or, these bi-attenuation elements that, this is actually some integer wave, right? And this is some, integer number of waves plus 90. So it's not a true 0, but it functionally is. So, but this again is 6 measurements, right? And we didn't want, 6 measurements when we could get away with 4. So, there's other ways just to, as an example that you can, think about taking a series of measurements of only 4 measurements that will be able to get you the full Stokes vector. And as I said, 4 measurements, but in a way that sort of optimizes your efficiency and optimizes balances between your sampling of the different Stokes components. And so sort of the optimal configuration for my 4-state modulation scheme for a liquid crystal, has a retardance that changes between 45 and 315 here, and has some strange numbers over here. But what happens is this, for each measurement, you get a combination of Q, U, and V, right? So you're not isolating with any one measurement, you're not isolating I plus or minus Q plus or minus V. You're getting them all mixed up in each thing. But again, this is just with just a linear combination of these 4 measurements, I can isolate either one of those. Turns out that A value here that you end up with is 0.5773, which is sort of the optimal efficiency, turns out that you can get. And again, if I look at my modulation matrix, this corresponds to, right, I have these different combinations here of Q, U, and V, but, I can combine those and isolate any one of those by selectively summing up the different measurements. So just as a side note, we're talking about retardances, and we mentioned liquid crystals yesterday and how what you're getting. And this is sort of the curve that the manufacturer provides of, as you apply increasing voltage, this is millivolts, so this is 0 to 10 volts. You start out with the very high retardants. When you have no voltage applied, all these molecules are aligned and producing the maximum retardants. And then as I apply, start to apply a voltage, it decreases here and my retardance goes down to some low value. As I said, it never gets to 0. So I can't use, a high voltage and get no retardants. So my better bet is to use, right, if I'm measuring at 8542 would be to find the voltage up here and give it 1 wave of retardants. And so, and then, choose different values here, and I can convert those, degrees, knowing my wavelength, I can convert to the absolute retardants, right? And this will depend on wavelength, which voltages are needed. But, it is nice in that sense that these liquid crystals, you're able to tune the retardants to different wavelengths and for any arbitrary sort of value of the retardants that you need, even these very strange angles. So It's 11:50. It's a good time to stop. We have some more modulation schemes to look at later, but it's probably enough for now. I will see if there's any, or do you want to do questions after lunch? If there's anybody has question now. Yeah, Ryan?
This might be something you plan to talk about later, in which case you can just tell me to sit down again. I'm thinking about crosstalk, which to my knowledge is when you're mistaking a Stokes V signal for some linear polarization signal. Is that something that like exists mathematically and comes out of this, or just like an imperfect implementation of putting this into practice?
Right. I mean, this is, materials will do that, right? I mean, here we've been talking about these perfect ideal polarizers and retarders and so on. There's a lot of other, that often comes up. There's a lot of other optics in the system. The classic one is a reflection off a mirror, where I send in unpolarized light and there'll be some linear polarization, right? We saw that yesterday, even, reflecting off a piece of glass. There's, reasons why you sort of generate polarization in the reflection. And so, yeah, that's the classic one in an optical system, that you'll end up introducing polarization, having this crosstalk from I, right, where it was unpolarized, incoherent light going in, and then, you generate some polarization in the beam as it travels through your optical system. And that's, yes, problematic. And yeah, so, there are terms in that, we had it back here in this matrices here, right, where we're looking, right? So all these are this crosstalk, the big ones, right? Again, I is often much bigger than the small little polarization signals we're measuring, so even if these are relatively small, you'll get this large, you can get a large contribution to your output Q if you have signals here. But there are also crosstalk terms between the other polarizations as well, or the other Stokes components. Yes.
Just showed that curve of retardance, given the voltage and so on. Seems like the one that you showed is very sensitive. So how do you build an instrument which can operate at more than one wavelength?
In more than one wavelength?
Well,
Yeah.
it's very sensitive to the response is very different in
Right.
the wavelength.
Right. Yes. So it turns out, yeah, I mean, that's, this is the curve the manufacturer gave me, provides, but you don't really, it's temperature sensitive. So it depends on the temperature, and these, you don't really trust necessarily what the manufacturer provides and so on. It turns out you can go back through your Mueller matrices here, right? And say, well, if I apply, and I, look at this for a minute, but, if I don't apply any retardants to liquid crystal 1, say, and let's see, there's one of the two that so right here, so Q, right, has no dependence on the retardance of liquid crystal 1, right? So I can sort of measure, I can vary the retardance of liquid crystal number 2, right? And with the polarizer in the beam, and I can measure the intensity as I vary that retardance. And at some point, right, if I calculate this out, it'll be crossed. All the polarization will be in, say, that vertical. And then as I change the retardance further, all the intensity, will be in the horizontal polarization state. And so I can sort of make a measurement as I change this delta 2 and determine what the retardance is, the actual retardance is for, as I, given the voltage that I change, what delta 2 do I get out? When does it go to 0? At certain places will tell me the retardance. Then I go back to my Mueller matrix and I say, okay, now I know, since, what my voltage to phase delay is for delta 2, I can apply a known thing here for, delta 2 in this, and, one wave or something, and then I can isolate and do the same thing with liquid crystal 1 and get out do a mapping then of retardants or voltage to the retardants and sort of reconstruct these curves, or at least a few points on the curve. You know, it's sort of when it goes through zero, or when the two, you know, one of the polarization states is maximum and the other one is minimized. You know, it goes through a sort of a oscillatory behavior. It allows me to sort of determine what the retardance is. But yes, it's an additional calibration that needs to be done. And I can do it for each wavelength, obviously, to calculate it exactly. Okay, there's no more questions. Let's break for lunch.
Anything anybody wants to discuss, whether it's related to the last couple of days or to what's coming down the pipe? The workshop,
next?
anything.
Yeah, this is I guess, not a super physicsy question. So we've talked about a couple of times about how in sort of optical systems, you are adding extra polarization that you may not want. Do the optics in the human eye create polarization in any way? Do any of the components of the eye act as like a polarizer?
My understanding is that the human eye is barely sensitive to polarization at all. I don't know whether it creates polarization, but it doesn't really detect it, as far as I know.
I don't think there is a preferred direction in the eye. It's like pretty. So it's a pretty bad optics, by the way. It's all the processing power that you have behind it that make it a viable option. But so I don't think that human eyes are polarizations. I think, for instance, when you look at insects, they probably have
They do.
so that they can navigate on the sky polarization.
And octopi and cuttlefish and all those animals that also see polarization. I don't know what they use
How
it
they
for.
do it.
Bees, they use it. Well, I mean, they have these slotted eyes to start with, and I don't know whether that has anything to do with it, but they definitely are able to detect polarization. And bees use it for it's to know where the sun is, essentially, and sort of navigate a little bit because the sky is polarized.
So you know that the sky is polarized, right, from Rayleigh scattering, which makes it blue because the scattering cross section is much higher in the blue than it is in the red. But also it is so the optimum polarization is 90 degrees off, because you can think of it, light comes this way, it goes that way. There's only one component that survives, right? The light oscillates this way, electrical field, and only this one survives in scattering. That's why you get look at through polarized glasses at the sky. You can clearly see when you rotate them that there is polarization.
This is going to sound like really arrogant, but this is like, I don't know, I've seen this a number of times now, and every time it gets a little bit easier to digest, but it seems like from the beginning when we're looking about the coherency matrix to like the end when we're learning about like the Jones formalism, especially when we're learning about like the Zeeman effect, that all this seems to more naturally fit into a formalism of like quantum mechanics. So why, I guess, maybe this is more of a statement than a question. It seems like, yes, it's more natural to learn this through the lens of quantum mechanics than trying to learn about it through like the phases of like an E&M wave, and then kind of going back and forth. Is it just because like QED is really, really hard? Maybe there's like a simpler way to like digest QED. 2 cents, I guess.
Well, I think quantum mechanics gets you to one place, but it doesn't give you the solution of the radiative transfer equation. It doesn't allow you to make an inversion code. There's more to that than just knowing quantum mechanically what happens. Practically, we take the results of quantum mechanics as a given, and we don't use it in these calculations. That's I think that would be putting the horse behind the cart. To be blunt.
It's probably a historical reason to some extent, right? Because a lot of the theory was developed prior to them.
So the explanation of quantum mechanics to what we use in practice came later than radiative transfer. So in a sense, radiative transfer was developed without knowing exactly where quantum mechanically things came from. But the quantum mechanical aspect is such a detailed description that it doesn't give you any practical applications, I would say. You may have different opinion.
No, my comment is that maybe in the next version we can try to do the same things, but the GDOS book.
Yeah.
And the problem is that the math involved there are really much more complicated, and everything is much more complicated to follow, much more complicated to understand. And you will see, I think, probably next week, that for understanding scattering polarization, if you use classical oscillators and things like that, it's very easy to understand. But when you compute it, you actually use quantum mechanics because you need that.
The other thing is quantum mechanics is kind of say it's not very intuitive, right? Quantum mechanics is if you use the wave function and the Heisenberg, what is it, the equation? Schrödinger. One of my German names wrong. Schrödinger equation. Then things work out. Just experimentally, you can see that it works perfectly. But why that is completely non-intuitive. While the semi-classical approach relates to things that we can intuitively understand. So I think that's one aspect. The other aspect is, I don't know how many of you have had any quantum mechanics, but in general, not everyone that attends these kind of meetings has had quantum mechanics. So start from, I certainly would not feel competent to start from quantum mechanics.
Neither would I.
Not many people decided that you
We tried that.
We tried that, it didn't work. But also for the optical devices and so on, I think that
You don't use the quantum.
You don't use the
route,
quantum, mechanics at all. I think that those are very well understandable, as for example, as Kevin was showing yesterday. The delays between the beams and so on. Yeah.
And so I just have, I guess, a comment to kind of just address yours a little bit. There's a little bit of a distinction between, using quantum mechanics in the sense of like, the atomic response to radiation, right? And incorporating QED, which is the second quantization. And I have read some papers about deriving the radiative transfer in, full QED, and not even taking into account things like scattering, it's incredibly complicated. And so I can point you to some references for that, but that's it does affect the radiative transfer essentially because it allows for kind of the non-local absorption of photons. But I'm not sure how relevant it is to astrophysical, like the regimes that we're working in. It's something that maybe if I ever have, 3 years of free time, something to look into, but it's really crazy.
When we solve the radiative transfer equation, we basically use macroscopic quantities. We use the microscopic, the quantum mechanically determined transition probabilities, but they add up into macroscopic emission and absorption coefficient, where you combine many different physical processes. So it's as much practical as well as that you don't gain much to go to the quantum mechanical details to solve the problems that we need to solve in this case.
But you still need it in order to do things right? So there's that trade-off.
Sure, you need
somebody to do the quantum mechanics.
It is very satisfying to understand from really basic principles what happens, but then you don't necessarily need to use those basic principles once you have some of the results that you go.
Yeah, exactly. That's what I mean. Like the classical approach, you need to correct it with the quantum results. beyond that.
Oh, okay. It's a good question about from the morning section is that it kind of they mentioned the LIS coupling of that of the well, just want to know is there any cases that we should consider about the JJ coupling?
For what coupling?
JJ coupling. Oh, yeah. So if there are, which
Yes.
kind of
Yes.
lines?
Even, sorry, I mean, it was your lecture, so.
No, but we actually need in practice. So, but I was going to ask you because I don't remember
No,
which was
so
the exact line.
in one of the lines of calcium 8542, that is one of the lines that is used in the VISP instrument at the DKIST. Certainly now, initially when we had only one configuration available, has several overlapping lines in the wings, and some of these lines have JJ coupling rather than LS coupling. So to get to use them consistently as instruments to measure the magnetic field, you need to apply the proper coupling. So it has practical. It's not just an interesting aspect. It's a practical
Where does that coupling enter your applications?
the lambda factor is different.
Yeah,
Yes.
okay.
Yes.
All right.
So-
That is the parameter
Yes.
that summarizes.
Yes.
Does it make a lot of difference?
I haven't tried. I doubt it, but I think we make more mistakes than
That, I see.
No, but to get consistent results, otherwise you have like a kind of a ringing with one line tells you this, the other line tells you that, because you're not using the proper constants in the one line.
The things you might want to discuss. Time is it?
No, 49.
We start in 5 minutes with Kevin. Anyway.
Yeah.
I hate this format where
I
we're
feel
all done over
feel
it,
very,
but
we
the
should see.
microphones work well though.
Okay.
Oh, I'm glad.
At least that.
He can't find anything good to eat at breakfast then. I don't know where he's going.
It's a pretty one. What does he want?
I'm holding you accountable to that one, Jen.
You can bring some bread with your
For
jam that you
breakfast?
made, your jam that you made.
Oh, yeah. We are discussing publicly breakfast choices.
All right, well, if there's no other questions, we can move on to Kevin when he's ready. Kevin was supposed to sit here and also
He
answer
doesn't like
questions.
these things.
I know, I get it. You can also ask questions. Oh, there's another question. Okay.
Cookies,
Yeah,
Mr.
please.
No, not
Breakfast
cookies.
jam.
Breakfast,
Breakfast
that's-
The question also come from the morning section. So when I showed some examples from the Hinode observations, I just found that there's one specific lines just between the two error lines located at 6302. And what's that line? Is I tracked some data site. It comes from the element number 19. Well, sorry, not 1990. So, but I didn't find any other information about that lines. So, and it seems only appears in the amber regions. And then, so you also say that? What's that?
I mean, you can answer, but then most likely just molecular lines. And those molecules appear only in the umbra because the umbra is colder. So outside of the cold areas, they're dissociated and they no longer produce absorption. And in the umbra, you still have these molecules. I don't know what molecules they are, but there's actually a bunch of spectral lines in umbras. And it's actually hard to see. In some of the umbras, it's really hard to see the Hinode lines because it's just all wiggles. And What was that? From the what element?
Which element?
Nickel
Nickel?
or
And nickel,
which one? Which element number?
90
or
90,
90.
yeah, I don't know.
I don't even know what that is.
No. My understanding was that they're mostly
Molecular.
molecular, but there
I would
could
think
be
so.
some other, you know.
Usually it's oxygen dioxide, usually, O2.
O2?
Well, those are telluric.
Those are telluric.
They're not in Hinode. The telluric lines are not in Hinode.
It's probably.
There's no O2 lines in
oxygen.
the, well, I'm sure there are O2 lines in the solar spectrum.
So if you were to observe those
So-
lines from the ground, there's also two lines that form in the Earth's atmosphere that are in
the-
between. Just right,
Yeah.
yeah, but that's not what you see in Hinode.
The problem with, speaking about O2, the same is true for H2, is that symmetric molecules that have two of the same atoms have no allowed transitions. They're very weak, the lines are always very weak. So O2 lines you would not see in the spectrum.
Because I don't, maybe it was TOI, TOO.
Exactly.
TIO, I think
Titanium
the TIO is longer. I think, the, in near, it's either. Now I'm gonna contradict myself. There might be C2, which are stronger lines, yeah. Or magnesium hydride.
But I don't know whether that answers your question, but most likely. And I've not seen anybody that has ID'd them actually, so
I did probably.
in the Hinode, yeah, they're mostly a pest for me.
Yeah, no, I spent some time seeing when you include the molecular lines, how much that throws you off in the determination of the, just using the, I think, center of gravity, and it messes you up quite a bit.
For the magnetic field, just using intensity and,
Yes.
yeah.
So they are not listed in the Bible, in the Moore list of
No, in the
lines?
no, that doesn't.
They don't have any
molecular
molecules.
lines.
No.
Well, they do, but
They do have
not that many.
molecules.
So not-
It might be, since it's only in the strong spots, maybe they don't have them.
Yeah.
Yeah,
I have a question. What are the smallest magnetic field that's using the T?
that depends on many things. Depends on the spectral line. The larger, some lines are more magnetically sensitive than others, right? So if you want to go for smaller magnetic fields, you want most sensitive lines. It also is going to depend on your spatial resolution too, and on your polarimetric sensitivity and extract. So I don't think I have an answer. It depends on it, whether it's fields along your line of sight or whether they're in the plane perpendicular, because the sensitivity of the transverse fields and the line of sight fields is very different through the Zeeman effect.
There is another answer to that.
You're going to give them a number?
Yeah,
Please, yes.
because what you are talking about is when you infer the magnetic field, but you can actually directly measure it. Okay, and the limit is the Doppler width of the line.
Yeah.
Because you could just measure the magnetic field with the splitting. It's the ratio between the splitting, the magnetic splitting, and the Doppler width of the line, the one that sets these limits for the detectability of the magnetic field directly in the measurements.
Used to, yes.
If you want to infer it, then there are a lot of things coming into play, which is signal to noise, spatial resolution, and a lot of things. And then you cannot have real fixed number. But I can tell you that if you maybe the maximum the weaker fields we can detect maybe can be 100 Gauss, something like that.
Well, again, it
Practice.
depends on where you're talking about a line of sight
In a
component.
line, yeah, it
but
depends,
you can
no?
go a lot lower,
But if
20,
you have,
10 Gauss, maybe depending on the sensitivity of the instrument.
it depends.
But
But
the
in my
vector field,
Mhm.
yeah.
But my feeling is you have fields is weaker than 100 Gauss.
Believe it.
You have an error bar which is 100 Gauss.
Yeah, I mean, typically with your noise levels, that just washes out anything below that. For the vector, the modulus of the vector field. Again, you can do better with the line of sight component.
I just remember one thing about like lines from, like if there would be a line from element 90, and then I don't know what line,
Don't know
what element it is, but 90 is very heavy atoms, so they would have very small thermal broadening. So there would be there should be, if there would really be a line from an element that high up in the periodic table, there would be very narrow lines because they don't have significant thermal broadening.
The problem is that probably the abundance is really low. But no, I don't know.
But even then, they should be very narrow.
Oh, yeah, it should be very narrow, but in terms of detectability,
sure,
abundance
sure.
matters too.
Like, yeah, for instance, barium, which is relatively heavy, much more heavy than calcium and magnesium. So it's a similar atomic structure, has very narrow lines because it's such a heavy atom. So that's how you can recognize also lines of the very heavy atoms.
I had a comment to what he said. Sorry, we'll go back
Yeah,
and
yeah,
forth
yeah.
topics. Oh, that's fine. The fact that is the ratio of the Doppler width of the line and the splitting that is the important one, right? And so this morning he mentioned that the splitting goes with lambda square. So if you go in the infrared, you are advantaged, but also the width goes with lambda. You know, it's not all in the lambda square of the magnetic field, but the width goes with lambda, so you still gain in going in the infrared. You don't gain
Only
square,
linearly,
but
yeah.
you gain linearly.
Yeah, that means the Zeeman splitting
Yeah,
is
the Zeeman splitting is-
easier to measure as you go to the infrared.
It's
But-
also why in the chromosphere, for instance, you have, even though the magnetic fields are weaker, so there it's already more difficult to detect, but also the line broadening is higher because there's more higher temperature, so more thermal broadening. So the lines are broader, and so the ratio of the Doppler of the Zeeman splitting over the Doppler width becomes smaller.
Okay, that's tough.
Let's let Kevin get started. We can continue the discussion tomorrow. Are you ready, Kevin? More or less?
Transfer.
So
1 minute. Okay. So if there's any other question, let's address it now, and otherwise we can wait till Kevin is ready. Quite good.
Another question, does
No.
the Zeeman effect ever break down where you can't use it for other effects that do the same thing? Or a difference that like different amounts?
Answer is yes. I mean, you're gonna learn some of it next week. Do you wanna?
Yeah, well,
Yeah.
that's the answer, yes. This is what, so you have the Zeeman effect is actually most of the lines we use in the photosphere. Some of the lines we use in the chromosphere, they have Zeeman effect, but many other lines we use already, Zeeman effect is not enough because the atom does not behave as we would like to, okay? And we have to take into account the Hanley effect or scattering polarization or the passing back effect, things like that. So we have to really solve the Hamiltonian just to get the proper the energy of the different transitions, okay? But in most of the lines, Zeeman is quite working quite well. I mean, and even in, I think in stars where the magnetic field is really strong, you can see how the spectral lines really split a lot. Okay, there are a lot of measurements about that. And I think it's still for very, very strong magnetic fields, many of the lines work well with the Zeeman effect. Okay, provided the levels, energy level are not crossing between each other, and then everything becomes much more complicated. Okay.
And correct me if this is wrong, but the passing back effect is not, well, I'm not going to go into the details of what it is, but it turns on higher field strengths, and how high depends on the spectral line, right?
yeah.
Simply.
So when the splitting of the magnetic levels becomes of the order of the difference in energy between the different say non-magnetic splitting, then you get problems that your eigenfunctions in the atom are not well defined and no longer valid eigenfunctions. And then you have to solve, as David mentioned this morning, then you have to solve the Hamiltonian of the whole system, and the eigenvalues change with the magnetic field actually, and also the splitting is no longer symmetric, so you get different problems. But it has to do with the relative size of the Zeeman splitting compared to the energy difference between the different magnetic sublevels.
And I was going to say, in my experience, the only line that I've ever had to deal with the Paschen-Back effects has been helium-10-830, which is a chromospheric line. When you go to the weak end of the field strengths, helium-10-830, just because it's a chromospheric line and it can produce polarization just by scattering, then you have this whole other world of scattering polarization. So polarization due to scattering, not to a magnetic field. And its modification by the presence of a magnetic field through something called the Hanle effect. That has a completely diagnostic route than the Zeeman effect. And that's another thing that we're going to see next week. But I guess in broad strokes, Hanle is for the weaker fields, and mostly just for chromospheric and coronal lines. Zeeman is for those intermediate fields. And if you go to really, really strong fields, you might need to dip into, solve for the Paschen-Back regime. And it could be, in detail, it's alive, broad strokes, that's kind of what you can assume. Move on to Kevin, otherwise he's going to run into time issues. Thanks for all the questions.
Yep.
This is great. This is fun to discuss things that are outside of the lectures and branching out into different places.
So we'll try to pick back up here, looking at modulation schemes. Yes, Roberto pointed out, and yeah, that the reason of these numbers in the 5773 is to try to get 1/√3 balance between all the different polarization states, the Q, U, and V. So that's why they're those strange numbers, and those are the Van Vleck angle. So they're not too strange of numbers. So this was, go back to our drawing here, we had these, one more. We were looking at this LCVR, these two LCVRs here. So they're, these two pieces filled with these molecules, and they're changed by applying electric voltage. So everything here is sort of fixed. There's another way to do modulation, right? Other than changing the retardance, or the amplitude of the retardance, but that's by to use a retarder and then rotate it in the beam. And so you put a retarder here by the incoming light, the exit of your telescope, as far up as possible generally. And then you go through and you send that through a fixed linear polarizer to your detector, just like with the liquid crystals. Same thing. There's two orthogonal polarization states. So to make maximum use of your light, you generally put in some kind of polarizing beam splitter and get both of those. And this is again a temporal modulation. Basically, the retardance is constant, but we're changing the orientation of the fast and the slow axis with respect to the incoming light and to that polarizer. So what does that do? We can go back and put up our Mueller matrices again, right? We have just this retarder, and then we have this polarizer back by our detector. So the retardance here, the delta is constant, and what's going to change with time is that theta, the angle of the fast axis or the slow axis. And so this is the combination here. I just have one of the linear polarizers here, not the plus and minus, but the idea is the same. And so you can go through and sort of calculate all these matrices out, and you get that the intensity coming out is this, again, a combination of all three components of your Stokes vector. You have the Q, U, and V, and your different combinations of the retardants here and the angle. And so as you change this angle, right, sometimes these things will zero out. Sometimes they'll be at a maximum. And so you can sort of, it will modulate Q, U, and V slightly differently as it rotates. And so Q, for example, is modulated at 4 times the period. So this whole rotator, rotates 360 degrees in a certain amount of time. Q is modulated every quarter of a rotation. U is also modulated at that same period, but it's shifted in time. So it's going to be, offset by half a period or a quarter of a period. And instead, V, you have to rotate in half a period. So you need half a rotation of your retarder to fully sample the Stokes V here, right? So, you get this sort of oscillatory signal between these three, and you can calculate then through, again, you're getting these different combinations of Q and U at each time step. And what you do is, you need to sample different modulation states or, different combinations here at different times. And so you take multiple samples during this rotation at different steps in the rotation, faster than the period of rotation, or, faster than this modulation rate. So you can sort of distinguish them. What that sort of looks like is, in this case, there are 8 different modulation steps here, right? You sample during the modulation of the rotation of your retarder. Your Q signal is being modulated here at 4 pi, and here also your Q, again, you see it's out of phase. And so you can take samples, measure your signal with your camera, in this case, at these different time steps, and then compare them and get combine these and get your Q and U. And then the V has this slower period, but you still sample these, get discrete samples during that. And so, your demodulation scheme, you get these 8 different measurements and you combine them, and you can figure out what Q, U, and V are from this thing, from your series of samples. The exact way this is modulated and so on depends on what the retardance is on your retarder. And, there's been work on sort of what are the optimal retardances you want in your rotating wave plate there. So this is, the other big way that we commonly modulate the signal in order to determine the Stokes vector from a series of observations. And as we'll see, this is what's often used in spectrographs, for example. They're often using a rotating retarder like this, whereas imaging systems tend to use something like a liquid crystal or a fixed, a fixed retarder that then changes its retardance in time. And we'll see sort of why that is tomorrow. Make a quick mention here about crosstalk. Ryan brought this up earlier. I just wanted to mention this, and again, we'll also talk about this sort of as a source of error tomorrow. But just seeing what another Mueller matrix is here, and where you have these reflections. This is sort of the light path for DKIST, and you can sort of plug in some different things, and you see some of these crosstalk terms. So I to Q here, for example, and then some other crosstalk here. So yeah, these same Mueller matrices can be used in order to characterize some of these other unwanted contributions or the effect of other optical components. And we'll talk about how that calibration is done and how you build up this sort of chain of Mueller matrices that you can use to characterize not just your retarder and your polarizer, but the whole optical system, because it all comes into play. So, you know, we've figured out now how we can actually use a retarder and a polarizer and, you know, sort of make these measurements and get the actual Stokes vector out. So that's great. But now, of course, this is spectropolarimetry, and we want to see how we're going to combine that with spectral information. And so we'll talk about these spectral discrimination, spectral instruments, and how we get that information out now. There is one part of solar physics where you don't need spectral information. You still use polarization, but you don't need any spectral information, really. You know, in most cases, you need the spectral line, or you want to observe over a very narrow spectral interval. So I just, you know, thought it was interesting. And, you know, we'll talk about scattering more next week, but the classic case of scattering in the sun is when you have a little free electron up here in the corona, right? And it sees the sunlight, and this wave, right? You have this wave propagating out from the sun. It's oscillating both in the transverse direction and in this direction across, right? But not oscillating along the direction of propagation. And so when it hits the electron out here, it scatters and it sets up polarization, right? In this direction, along perpendicular to the observer, right? And also along the line of sight, but we don't see that, right? We're not sensitive to that direction of scattering. And so what happens is now, when we look at the corona, we see clear polarization signal from the scattering of the electrons. And since this is just broadband continuum scattering, you don't need any spectral information. You can just look in, you know, over 1,000 angstroms and see this effect, right? And, you know, this is what produces the white light corona, is all this scattering. And if you measure this, right, there's, you can see that there is polarization in, you know, all around the sun, sort of in this tangential direction, as you expect from the, you know, scattering from the electrons out there. And, you know, you can use that also to separate out the other contribution, which is the F corona, which is sort of scattering from dust that's much farther away from the sun, you know, but sort of light that's gone backwards from the sun and then is scattered back towards us, you know, will also be integrated along that line of sight. And you want to sort of separate that out and understand, just separate out the electron corona. And so polarization is a way you do that, but you don't need any spectral information. I'll ask one question. Let's see if anyone. So, you know, we see the corona extends, you know, far out. We can see, you know, K corona here, but then these, you know, material all the way out. Does the polarization, the amount of polarization change as we go further away from the sun in the K corona? And if so, which direction? Is it getting more polarized or less polarized? Go back to this one here. If it answer it next week, it's gonna be important next week. I bring it up now because it's really easy to sort of picture it as electrons, and they're further, you know, far away from the sun. So, you know, there's a hand up. Yeah. Right. Right. So when you're down here, you're illuminated by this whole star light coming from different directions. And so there is some illumination, right, that's coming from not straight on like this that produces the perfect scattering, but it's coming from behind or this way. And so the sun, you know, is large compared to this poor electron that's, you know, 50,000 kilometers above the surface. But as you're several solar radii away, the sun sort of shrinks down into more of a point source. And so you get, you know, a purer scattering. And so, you know, you can see this gradient in increasing polarization away from the sun in the corona. So I think I need to switch presentations now. And now we'll look at some specific sort of instruments for measuring. Now we want to measure the spectral information, right? And, you know, thanks, you know, using a lot of things that Bruce Lights provided. So thanks to him for all the slides. So, you know, extracting spectral information is a little bit like getting the circular polarization. It's kind of hard because it's buried in there, right? We need to, you know, separate frequencies that are different by, you know, a part in 100,000 or less, right? In order to resolve these spectral lines. And so, you know, we need to find a way to separate out, you know, frequencies that are very closely spaced, you know, in absolute terms, and separate them out and sample them differently. And then we have this problem that we want to observe the whole surface of the sun at once, right? It's not just a single point. The sun, as we know, has these, you know, large coherent structures that interact with each other, and so we want to measure these things across the surface. So we want our X and our Y measurements, right? But we also need the lambda. So we have these, you know, 3 sort of immediate dimensions that we want to sample at once, and most of our detectors are all 2D, right, in any real sense. So, you know, we need to find a way to take these 3 dimensions and sort of map them back onto our 2-dimensional detectors in a reasonable way. And then, as we say, you know, it's not really just 3D. You know, we're also talking about the polarization here, of course, which is, you know, the Stokes vector. It's another, you know, four different layers of the cube, or another dimension. You know, it's restricted into those, you know, 4 Stokes parameters, but it's still another dimension to sample. And then there's the temporal dimension, right? The sun is evolving continuously. We want to see this evolution, so we have to sample things in, you know, fairly rapidly in time as well, you know, both in order to understand them and just because our sampling cadence, you know, we can't let the sun completely evolve and change while we're observing it, or it just further complicates our hope to, you know, make a reasonable interpretation. So, you know, how do we slice up this cube? What does it look like when we take slices in different directions? You know, we saw the image there. You know, if I slice it and look in, you know, Y and lambda now, instead of X and Y, now I see these spectral lines going across here, right? And so these are the 2 6301, 6302 spectral lines. Here's the sunspot. You know, you see it's very dark there in Y and across the spectrum. And now if I, you know, go to this, you know, to a different Stokes state here, now I see the Q polarization, which looks, you know, different. And then U and B. So I want to be able to sample these, you know, 4 different Stokes parameters. And I want to, you know, do this continuously, rapidly, and at, you know, fairly high precision. So how do we go about that? You know, another way we can step through in X and Y and lambda. We'll see this with some different kinds of instruments, you know, and I can look, and these are different, the Stokes V, Q, U, and V at different wavelengths here, going through the line. So we have this cube, and there's a lot of different ways people have come up with how to slice it and dice it in sort of different ways of multiplexing, of layering up different dimensions. So here's our cube up here, right? We have X and Y, the sunspot here, and then we have this rainbow indicating all the different wavelengths we might want to sample, you know, going through a spectral line or something. So, you know, a lot of you are familiar with what we call, you know, filter graphs, which sort of have a narrow pass band in wavelength and then provide a full image in X and Y, but just through this narrow pass band. Filter graphs, it was a term, coming back, we'll see from sort of a Leo filter kind of approach. Now it's easier to get very high spectral resolution, comparable to a spectrograph. So, sometimes we call this imaging spectroscopy because we're taking an image, but high, spectrally resolved. And there's a lot of different instruments that, that do this, that have, on the ground or flown in space. And so then you can sort of sample here in time and change that pass band, and you can sample the different wavelengths and build up your cube that way. We'll take a look at slit spectrographs, which is, another classical way to get the spectra, and where you're building up you have a Y and a lambda, and you build up your spatial dimension in time. Then there's other approaches, subtractive double pass, mixing the things all up in a single image, or a multi-slit spectrograph, where basically you're sort of taking your single slit approach and being able to, use multiple slits at once. So you're making a little more efficient use of your 2D detector by not covering as much spectral range that maybe you're not as interested in, and using that to get a little bit more spatial information. The other approach is to use a slit spectrograph again, but then find different ways of taking your image and sort of, instead of being forced to acquire the data or, spatial points that are lined in one dimension along the slit, you can sort of pick out which data points you want to use across your image and remap those into a slit, either using fibers or using a series of small mirrors with an image slicer, or using something called a micro lens array, where you make multiple images of different points in the field of view and project it onto your grating. And so you get all these different individual little spectra there. So, we'll take a look at some of these. I will point out a lot of these are used at nighttime too. James Webb has a micro lens array approach it's using, or it's actually, they use a bunch of little doors in front of in the focal plane that they can open and close. And then they can, pick which light goes through and goes to the grating. And so they get a bunch of little spectra like this scattered across their image. Or they use fibers to pick off, distinct galaxies. They have this issue where the field is very discrete. They may want to sample 100 galaxies scattered over a large field of view. And so they can use individual fibers and place them, in the position of each sort of galaxy in the field. We have, we want to get basically a filled field of view. So we have, we don't want individual points picked out of the field, but we want to get, a densely sampled field of view and imaging and spectral information at the same time. So in that sense, it's a little bit different, but we're all trying to do the same thing, combine all these different kinds of information. This is like before, but it's in a table form. Discussing the different kinds, filter graph, spectrograph, and these integral field things. And you just see there's a lot of different ways you can do your polarimetric sampling temporally, as we were discussing with the liquid crystals. You can do spatial modulation, where you're sort of getting multiple modulation states at the same time. And then, build these things up in time, most of them, right? They were all sort of sampling at multiple times. And, one final look here at just all the different, a lot of different roads you can follow in building your instrument. This again from this paper by Glacius and Feller, where they sort of looked at all the different instruments and different spectral ranges. And, all these have sort of different approaches. Some are in space, some are on the ground. And there's just a lot of different instruments and different approaches. The underlying reason for that is there's no one best way, right, to do this. It depends, a lot of it depends on what you're trying to do. Different scientific needs have, place different constraints on whether you need the sample, at a higher temporal cadence, if you need more spectral information, and so on. So it's, you know, the reason there's so many different options is because the sun is doing so many different things, basically, in different ways, and we need to, you know, have different ways to sample that. So we'll start with the classical long slit spectrograph, right? This is, you know, how spectroscopy was done, you know, on the sun for a long time, where you just basically, you know, you put a slit in at an image plane, you send a narrow slot of light through to a diffraction grating. And what happens at the diffraction grating is, you know, you make multiple reflections, distinct reflections, back in a certain direction, right? And so your image comes in and then is reflected backwards multiple times, right? These gratings have hundreds of lines per millimeter. You know, the more lines, sort of the better your spectral resolution is. And what happens is all those different reflections, each one has a slightly different phase delay. And so they all interfere differently when they get down to your detector. And so you're making a whole bunch of individual reflections. Each one has a slightly different time offset. And so what happens is you get destructive interference at all but, you know, a very specific wavelength. And what happens is that wavelength where you get where you get the constructive interference, where the light persists, depends also on the angle, right? So as I change that angle, a different wavelength will be, you know, constructively interfered, and everything else will disappear. And so as a function of angle here, I have different wavelengths that I'll sample at different parts of my detector. And so, you know, this is an old, you know, spectrograph slit image. You see all the different lines. You see, you know, different things going on along the slit. I believe, you know, there's a flare going on here in the calcium K lines, and, you know, nothing going off here. So I get a little bit of spectral or spatial information and a whole lot of spectral information. And so, you know, this kind of observation is very valuable when you want, you know, good spectral information over a broad range. So, you know, these things are, you know, they've been used for a long time. They're relatively simple sort of optical systems to some extent. And, you know, here's a drawing of a grating based slit spectrograph. You have a grating here, right? The light comes in here and goes to the grating, where it then is reflected up into different channels, this red, green, and blue channel over here. So you can sample this thing, the image here. And then, of course, you can move that slit in space, right? Your slit is taking out a piece of your image, but then I can move that slit, you know, take one observation, move the slit to a new position on the sun, take another one, and slowly build up then that third dimension. You know, I get the Y and T in one spectrogram, and then as I build up multiple images, I get the whole data cube. That does take some time. You know, just the mechanical moving of the device is one thing, and then there's, again, based on scientific needs, sometimes the integrations are long, so sometimes it can take you know, minutes or an hour to build up the whole 3D cube with this approach. And, you know, that the drawing here in this picture is of, you know, the current best thing in slit-based spectrographs, the VISP on DKIST. So these are the three different spectral channels, and then the grating is down here to feed those. Let's see. My movie's gonna play. Oh, there it is. I don't know. Nope. Hey. No, doesn't give me the play option. All my movies. Yeah, I don't know. Won't let me click to start the movie, but this is, you know, it just sort of shows there's a series of movies showing the way that these different instruments would sample. So here, gonna go on its own. Here you see the, the spectral line coming down here, the IQU, the QU and V, different Stokes components. And, you can then scan through and build that up. So, these are, great instruments. They, one thing you notice is they get, here's the spectral line. This is already sort of artificial, but there's a lot of continuum out here, right? What's happening here, I mean, this is a somewhat extreme case with these very large polarization signals, but, what I'm really interested in is the spectral line. And, sometimes, my detector is a couple thousand pixels across. I'll get, 5 or 10 angstroms of continuum out there, which I'm not really interested in. For some cases, it might be useful, for these large velocities and so on. But often the drawback is you're getting a lot of spectral information that isn't, particularly useful in getting to, a scientific answer. And so there's a, sort of inherent inefficiency sometimes in sampling, using a lot of your pixels, right? This whole thing is how do we best use our limited number of pixels we have on these detectors? And I'm using a lot of pixels, to measure continuum where I don't have spectral line signatures. So another approach then is not to use a grading where I'm getting interference from reflections or, from these multiple reflections off a single grading, but I'm setting up my interference by having multiple reflection inside a cavity. And so now I'm getting, right, sort of like the diffraction grading, I'm getting multiple beams coming out, each with a, with a delay, and then those line up and have a peak transmission at a specific frequency, and then all the rest are sort of damped out, destructively interfere. So these are nice. We can make them fairly accurately now in terms of getting a spectral resolutions approaching that of a spectrograph, and having a fairly large spectral range, right? All of these things will have a periodic transmission profile. The grading sort of has that. There's multiple orders, but it's easier to separate out. These generally have peaks that are fairly close together, even after, for a single Fabry-Pro, they may only be an angstrom or so apart, and we'll see how we can deal with that. But we're getting, good spectral resolution comparable to, a fairly high resolution spectrograph. So one drawback is, we have these multiple beams coming out, which is true, but, these have gone through this cavity twice now, have had several reflections. And so the transmission of these beams, because there's some absorptive losses on each reflection, the reflection of each beam is slowly decreasing, right? So unlike the grading where I have many reflections, all of equal intensity, here I have many reflections, but with a slowly, a decreasing intensity. So instead of a nice Gaussian profile that I get if I combine a bunch of reflections off a diffraction grading, here I end up with a more Lorentzian profile. So I have these broader wings in the transmission profile, which is, is basically, it's a little bit worse in terms of the spectral resolution that you can, effectively get, or at least you have to be careful in, quantifying your spectral resolution, but that is a difference between these two. And so, as I said, we've done this. Here's a picture of our old friend Ibis here. We have these Fabry-Pros. As you might imagine, this, this spacing is very small, and I'm, my interference that I'm setting up is based on how thick that, the distance between the cavities, right? That's what's introducing the delay. And so if that cavity changes, by a fraction of a wavelength, it's going to end up changing, where your interference is occurring. And so these have to be temperature controlled, to, a 100th of a, tenth of a degree or better in order to get a stable transmission profile. And as I said, they have these, a single Fabry Pro has a single peak, but there's another one right out here that's just a couple angstroms away. Or in the black case, these are less than an angstrom away. So I only want, in order to tune through a line, spectrally sample a line, I just want one transmission peak and not all of these. So we combine two of these in series with slightly different spacing. So I get this black profile is the transmission profile of a single Fabry Pro. I layer that up with another one that has this red transmission profile, and you see I attenuate most of the peaks out here. And you can see this now. Now this is plus or minus 4 angstroms around the peak. Now I'm going plus or minus 10 angstroms, 1 nanometer around the peak. And so now I see in this logarithmic scale, I've attenuated all these side lobes mostly. And it's not until I get 6 angstroms away in this case that I get another peak, and I can just use an interference filter to attenuate that, and I end up with a fairly high spectral purity and transmitting just that central profile. And then the trick is this, I can change that cavity, right? This the spacing here depends on a couple of things. It depends on either on the distance between the cavity, as I said, or it depends on, for some solid state, like the lithium niobate, they can be attuned electro-optically. You apply a voltage and that sort of effectively changes the index of refraction. And so you can tune these spacings and then change the wavelength. And what that lets you do, and this movie isn't going to play either of it, is move that transmission profile through the line. So I pick out individual spectral samples in my line profile, and I sample through and build up, my image or my data cube by sampling in wavelength. And one, efficiency there is I'm spending, I have all my pixels on my detector are sampling in spatial dimension, and are densely sampling the whole image space, right? And I'm going through the line, right? So I have, 1 million pixels, or in the case of DKIS, 16 million pixels sampling in space. And I'm just sampling, I only need, typically, 15 or 20 points through a spectral line profile to characterize it and understand its shape pretty well. So, I'm using that spectral sampling, which can be, I need fewer points and can be sparser, and spending all my, using up all my pixels on that dense spatial sampling. So, that's, for some purposes, that's a more efficient way to sort of multiplex in spectral dimension and get, the full spatial information. The Fabry Pro Fabry Pro's been around for 100 years. It's sort of come into its fore in solar physics in the past couple decades. Before that, they did this same sort of thing using LEO filters, using birefringence. Again, talked about that yesterday. And basically by using different pieces of quartz or calcite, right, that has this birefringent property, and putting it between two polarizers, you end up, you can get, you get a transmission profile through a wavelength dependent transmission profile. That retardance that you're seeing is wavelength dependent. And so as it goes through, right, at some wavelengths, it's a quarter wave and it's going to be completely attenuated, and some it's not, right? It'll be, a single wave, and so it won't be attenuated at all. And so by, properly choosing the thickness of my birefringent element here and putting between two polarizers, I can end up getting a sort of a periodic transmission through this piece of calcite through this filter. Then I do that again with another piece of calcite, say, right? And I apply the same thing, and with a slightly, changing the thickness here, so I get a slightly different period. And sort of like that Fabry Pro again, where now I'm sort of attenuating, alternately, attenuating these side lobes in the transmission profile. And so you can end up with, you can put these now, put 4 or 5 of these together in series, even more than you would do with the Fabre Pro, but you get, you start out and you end up, being able to isolate a sort of a single transmission peak, and then you're able to use a broader sort of just an interference filter to isolate just that single peak. Now, obviously, this is somewhat complex optically, right? I mean, you have a whole bunch of polarizers in series, and then these calcite. Transmission generally isn't very good, certainly in these, in the original calcite-based approach. And you might say, well, you could do this with calcite. We have liquid crystals now. You can do the same thing, right? Just another kind of retarder. And you can, do the same thing with liquid crystals. And there are sort of liquid crystal-based LEOs. And I think that's what's being used in the Chromag, right? I was using a liquid crystal-based LEO filter. So yeah, this is, you showing how you can put these different elements with different periods, and they sort of add up into a single transmission peak. And this is how you would tune it by, putting this quarter wave plate and then rotating your polarizer. So it's, it's another kind of filter graph. The third way, most popular way to do sort of imaging spectroscopy, as we were saying, is, get a narrow passband through a 2D image, narrow spectral passband in a 2D image, is a Michelson interferometer. This is what HMI uses. So, you've all used one of these probably, or if you ever used HMI data, you're using a Michelson interferometer. This is, the classical Michelson interferometer is the 2 legs here, and then you can, shift those, the delay between the 2 legs, and you end up with these interference patterns, right? And again, that's just another way to get this interference. We obviously don't want a single point like you would do with a laser, but you can actually do this with a whole image, put a whole image through the Michelson interferometer and get this. What's nice, the reason that HMI uses it, that Gong uses it, is that these can be very stable. They don't have they have just a single a variety, not one glass piece, but several glass pieces that are all sort of connected together. So they're stable, so nice to put in space, nice to do helioseismology with when you want a nice stable passband. And you can optimize this with polarization and put in quarter wave plates, so you're getting the reflected polarization out. And by having that quarter wave plate and with a rotatable linear polarizer, you can actually tune then this the Michelson interferometer, and so then you can change that passband and get different wavelengths. And so they sample through the 6173 line with HMI, for example, with this approach. So yeah, there are drawbacks to these any of these imaging approaches. They are sensitive, to temperature. You do need to keep them controlled, because you are, instead of diffraction grating where you're just reflecting off a bunch of images and they're all experiencing the same, path through the air. They're all reflecting off the same, once off the same mirror or the same diffraction grating. Here you're looking at multiple reflections. And so any changes, in there is going to change path lengths and cause things to drift. Spectrographs are simpler in that sense, but as we saw, they have other issues. Just a different way to slice it up here. There are now, though, some what we call hybrid discriminators, right, where we try to combine all 3 things at once instead of just getting, X lambda or XY and then tuning in wavelength. you know, I mentioned some of these ways, the image slicers or micro lenses where we can try to get samples of the cube of, you know, a portion of the whole cube at once. So the image slicer, how does, you know, that work? You know, I take a mask here and I divide it up, you know, in this case, sort of with, I can do with mirrors where I reflect each one of these yellow portions would be a mirror with a slightly different angle to reflect off in a different, slightly different direction. You could also think of it with fibers. We do this. I could put a series of fibers, fiber optics there that would be arrayed along these lines and then would be go out to the input of the spectrograph slit. And so in that way, I sort of remapping it onto the slit. And so what happens here, you know, it sort of moves all these things over onto the slit. And so then I sample, you know, that all goes through the slit, gets dispersed, and I measure it. Then I have the task of them, you know, remapping these things back onto my proper XY space, right? I've sort of put them in this one-dimensional slice now, but then I have to go back, whether it's fibers or a mirror array, I need to go back and sort of figure out where each pixel should be back in my image plane. So we have, you know, examples of this that were developed at the Dunn or in the Canary Islands, and now we have a fiber-fed version available. This movie works at DKIST, where you take this, you know, image, and you get, you know, pieces of the whole cube at once. Now we still have the problem here, right? I mean, these are great, but we only have a certain number of pixels, right? And if I have 1 million pixels and I need, you know, 100 or, you know, 1,000, you know, pixels for each, you know, little spectrum from each spectral point that I want to sample, then I'm limited in the number of spatial points I can, you know, I can sample at the same time. And so, you know, what you end up with is a fairly small, you get a whole XY lambda at the same time, but of a very small region of the sun. You know, in the case of DL NERSC, because of the high spatial resolution of DKIST, you know, if you want to exploit that, you end up sampling just, you know, a couple arc seconds square portion of the sun at once, you know, whereas with some of the other things you're sampling, you know, 60 arc seconds along the slit or a 60 arc second square. So, you know, and the answer to that, then if you need to, you know, see this whole, you know, sunspot in this case or some extended structure, is you then have to sort of tile up and get multiple samples. So, you know, if you do need an extended area with this kind of instrument, you're back then to sort of a temporal sampling, taking pieces of the cube each time. But, you know, again, if you just need to look at a single bright point, then, you know, you can just stay in one place and sample continuously. So, you know, there's a lot of ways, other, you know, even more complex ways of doing some of this hybrid sampling. You know, people like Craig DeForest and Charles Kankelberg have done things with stereographic spectroscopy, where you're actually sort of not getting a single, you know, slice through your this XY lambda cube at one time. You're getting a couple, right, by sending in this image through the grating and looking at different orders at once. And you can use interesting techniques to try to tease out then all the information at once. You know, not quite as direct as just, you know, imaging a slice of this cube onto your detector. And, you know, sometimes it's hard mixing, getting as high of a spectral purity when you're doing some of these things. You can, you know, certainly sample in the spectral dimension, but the spectral purity is hard to get to the same degree as you can get with a grating spectrograph or with a Fabry-Perot. And yeah, I think I will stop there, discussing all the different ways people have skinned the instrument cat, so to speak. And then so tomorrow we'll take a look and see when we use these instruments, what are the challenges? We brought up the crosstalk. There's a lot of real world things that we need to that come in when you actually apply one of these instruments and do real observations. And so we'll go over that and some of the detectors that we use. There's some specific sort of detector technologies that help in measuring polarization. So with that, I don't know if there's any questions. What people's favorite instrument is? Did I? Yeah.
Well, Kevin, my question had to do mostly with like the slit jaw imaging, especially if you're trying to build maybe with slit imaging, building a big picture. You mentioned, it takes some time for the slit to kind of like move along. What are what are some of the issues that would introduce in terms of like sun is constantly evolving, and you said something maybe like sometimes it's an order of like minutes.
Right. Yeah, I mean, you're not getting like a single snapshot of the sun generally. You can do a very narrow scan with the slit, right? I mean, so you have a few options. You could, you can take the slit and leave it at one place, and we call that the sit and stare, and you just get continuous observations, but you have no information in that other spatial dimension. You can do, a very small sort of raster where you're sort of evaluating what's the time scale of the evolution that I'm kind of looking at. Is it a minute? Okay, how many steps can I do within a minute? So I can cover this many arc seconds and try to get a little bit of spatial information, but try to match to that, sort of the evolutionary time scales you don't want to get confounded by. Or you can, just, it is what it is, and you scan, right? And we're seeing scans with DKIS that can take like an hour or more to scan a region. And so, yeah, you're not getting a consistent picture. Every sample of the slit is adjacent to one that was just obtained immediately before it. So within, as you're sampling, there's a sort of coherency among the points that is maintained, right? You're not sort of randomly putting the slit in different parts. So yeah, there's, that is a problem, but, and, that's sort of tied to the signal to noise you want, as you'll see here, and, trying to do the spectropolarimetry of these chromospheric lines or measure the Hanley effect or whatever you need. You have to decide whether that loss of understanding the evolution of, of the region is worth getting the high enough signal to noise to make a measurement, and some things like the, large scale field of the sunspot aren't going to change, over that time. Another option is to sample your slit sparsely, right? And then you're sort of taking a more of a random sample across a region, and not worrying about getting adjacent points or getting the whole densely sampled, sort of like the spectral sampling. You can sample at a different, the slit doesn't have to be continuously moving to the adjacent point.
So I have a question about like Fabry-Perot instruments. So I've noticed kind of in practice that they tend to go out to, a bit into the near infrared, like out to like the calcium infrared triplet,
right?
And not too much farther. Right. Is that just because of the transmissibility of the kinds of optical glass that are normally used for the Fabry-Perot itself, or is there some other kind of fundamental reason why they aren't applicable in the sort of like, mid-infrared?
Infrared. I think it's mostly a question of just what people have been interested in originally. There's a wealth of sort of spectral lines people knew in the visible, and but there's no real reason why it wouldn't work in the infrared. I mean, there is an infrared Fabry-Perot instrument at Big Bear that uses a Fabry-Perot. So, you know, the glass and the coatings, it actually gets easier as you go to the infrared in terms of, you know, you need for example, there's some constraints on these Fabry-Perots. They need to be fairly optically flat for a variety of reasons. Right. I mean, you know, and glass becomes opaque, you know, it's out at, you know, a few microns or, so, you know, that's not really an issue. In fact, someone should build an infrared Fabry-Perot instrument to sample the helium-10 830. But yeah.
So the proposed European Solar Telescope, whether or not that goes ahead or not, what is that hoping to offer that DKIST and these other instruments that you talked about here? What's that hoping to offer that these instruments can't?
It's been a while since I've, you know, informed myself of the, you know, latest capabilities. I mean, I remember one thing at the time was there would be a lot more instruments all running at the same time, and a lot more data. So, for example, on DKIST, we have like 2 broadband imagers running at once, and there's 1 Fabry-Perot tunable filter. You know, I think originally, or, you know, it was discussed there'd be like, you know, 5 broadband imagers running and 2 or 3 tunable Fabry-Perot systems running at the same time. You know, which obviously with VISP, right, with the grading spectrograph, I can observe, that's another advantage. I can observe 3 wavelengths at once simultaneously through my instrument, whereas something like a Fabry-Perot or the, you know, Leo filter, I can observe 1 wavelength, then I go to, you know, can observe another one, and so I have to do them in series. You know, one way around that is to build 2 or 3, and then you can observe 2 or 3 lines at the same time. You know, there's cost and complexity associated with that. So,
Shall we start? So today I will talk about a little bit different things than so far we've talked about, more like a practical application. We've covered quite a bit of ground with David and Kevin, explaining what polarimetry is, how we derive the radiative transfer equation with all the Stokes parameters from first principles, and how we measure the Stokes parameters. But we haven't really talked about spectral lines themselves. We've more or less assumed that if there is a transition, atomic transition at a certain wavelength, that somehow this spectral line will appear in the spectrum. That's not, when you think about it, that's not obvious. For instance, why are most of the spectral lines that we see in the visible, why are they absorption lines? Does anyone know why are they absorption lines? And as an addendum to that, why do we sometimes have emission lines? As she said, what? She's itching to answer. Okay. She's heard this talk many times, so she knows. So I mean, there you have it. I mean, basically, we have absorption lines because I'm going to give it away right away. Is that in the core of the line we have higher opacity, and therefore we are sensitive to higher layers of the atmosphere than in the continuum or in the wings. And in higher layers, since we have in the photosphere, we have a temperature that generally decreases with height. We have lower temperature and therefore lower intensity. That's why we have absorption lines in general in the photosphere. It's as simple as that, but it's not. The mistake to make is that to say, well, the opacity or the transition probability is much higher in the core of the line, so therefore we absorb more. That's not right, because you also emit more at that wavelength. So that's not why you have an absorption line. You have an absorption line because you are sensitive to a different layer in the atmosphere, and typically in the photosphere that layer is higher and cooler. That's why you have an absorption line, right? So that's just a small, but we will cover. We have quite a bit of ground to cover. So we've seen from David how you derive the rate of transfer equation from first principles. I will take a more phenomenological approach, where they have absorption and emission coefficients are basically macroscopic quantities, and we'll just write down the transfer equation, and we'll show this the solution of the transfer equation. And then we'll make a very simple assumption. The Milne-Eddington is basically an approximation to the radiative transfer equation, where you make the assumption that all the quantities don't vary with height, except for the source function, which is linear with the optical depth. And if you make that assumption, you can actually solve analytically the radiative transfer equation and express the shape of the spectral line in terms of just, if you have no polarization, in terms of 5 quantities. And this allows us really to, and those quantities are dependent on the properties of the atmosphere, like the temperature and the velocity, the thermal width. And so we make that assumption. It makes it a very easy way to make inversions, where with an inversion, I mean, I take the shape of a spectral line, and from the shape of the spectral line, I want to determine the properties of the atmosphere that I'm looking at. And when you make this simple approximation, then the quantities that on which the line profile depends are directly related to the properties of the atmosphere. So by making a simple fit to these parameters, we can actually determine a first guess of the atmospheric properties. That is what the Milne-Eddington approach is about. Let's see if this works. Yeah. So let's see if I can get this started. Yes, I really like this movie, and I've shown it almost in every talk that I do about solar radiative transfer, in the sense that this is observations of Hinode in 2 different wavelength bands. The blue is basically the G band, and it shows the photosphere. It shows that the atmosphere is very dynamic. It shows that in the lower layers, the atmosphere is mostly determined by convective motions. Then when you go up, you transition to the yellow, which is the images that are obtained in the calcium line, calcium K line, which forms in the chromosphere. It shows a very different structure. You start to see the effect of the magnetic fields much more clearly, except for, of course, the sunspot, which is there because of the strong magnetic fields. But let's see if we can play it again. Yeah. So you see that the atmosphere, when you go up in height, changes really in character. Also, it shows you that at different wavelengths, you see different layers of the atmosphere. So if you, depending on what layer of the atmosphere you want to structure, you choose your spectral lines or your spectral phenomenon that you want to use. And it shows that the atmosphere is very dynamic, that we cannot just observe and sit there for hours to collect enough photons to have a very high polarimetric sensitivity, because the atmosphere changes on it. We can only look for a couple of seconds in the chromosphere actually before it changes. So that limits actually the polarization accuracy that we can achieve, because we cannot just sit there and count photons, and every 10,000th of a photon is the one that we need with the polarization that we need to measure. So that kind of sets the scene of what we're talking about. Of course, we now live since earlier this year in a very exciting period in solar physics, in that this decist is actually doing observations. Oops. Should we hold the play? This is one of the first slide images from the decist, and it shows very exciting high structure, high spatial resolution structure. Ideally, you would want to go to every pixel in this image, have a spectrum of the spectral line that you prefer, and do an inversion, determine the physical properties of that location in the atmosphere. So this school is basically trying to tell you how to do that, or how to make a start of doing that. And the resolution and the wavelength resolution, the temporal resolution that we can now achieve with the instrument at DKIST, it's really amazing. You think about it, the biggest telescope that we used before had a 1.5 meter diameter. This is almost 3 times as big. So the spectral resolution or the spatial resolution, but also the temporal resolution, because the instruments are newer, the technology is newer, is so much better than anything that we had before. Hopefully. And I think it is. So one of the things that, or I'll make a short list of the things that I want you to come away with from this talk. One is to realize that opacity varies with wavelength. Of course, it varies strongly through a spectral line. We can use this to our advantage by using it to probe different layers in the atmosphere. Higher things with wavelengths with higher opacity form higher in the atmosphere, and things with lower opacity form deeper. So they give you different information about different layers. And again, wavelengths with higher opacity sample higher layers. Opacity varies very strongly across the spectral line, so it samples very different heights in the atmosphere. And an absorption line occurs when the intensity in the core originates from a cooler layer than from which the continuum originates. I told you before, and that's why we have absorption lines. When you want to make a measurement, you want to measure the magnetic field, that determination is strongly dependent on the model that you use. I told you that you can make the simple approximation like in the Milne-Eddington approximation, where you assume the properties do not vary with height. And in that case, you can make a very analytical solution of the transfer equation. That is the model that you use, and the result that you obtain is dependent on your choice of that model. Similarly, if we use a more advanced code like SIR or Desire, which we will talk about later, where you have actually, you get results that vary with height, you still use a certain forward calculation that includes some physical effects, but it neglects other physical effects. That's a choice, that's the model that you make. And the result that you will obtain will be different if you use different models. You will not measure the same magnetic field, right? So be very aware of that. As I said, the Milne-Eddington is one such approximation, and is as such is a model. And I told you before in the introduction that the Milne-Eddington is a parameterization of the solution of radiative transfer in terms of some of the physical quantities at one height in the atmosphere. And so the result that you obtain will be some kind of average, and it's very hard to determine exactly what kind of average it is, because it depends on how strongly quantities varies with height. But it is some kind of average of the actual values in the atmosphere. And you have to take it as such. And so if we make a fit of this parameterization to this observed spectra, this will yield the values of the parameters, and therefore is an inversion. Is one of the simplest way to do an inversion. Now, to just give you an easy to understand or easy to appreciate example of how we can use a model to determine physical quantities. This is the spectrum. It's not an observed spectrum, it's just a simple calculation of the sun for a large range of wavelength. You see from all the way to 0 to far in the infrared, right? And you see it's more, all of you know what a Planck spectrum is, right? I'm assuming what a Planck function is. Yes? You see that this more or less is like a Planck function. And let's see, this is the Planck function for the effective temperature of the solar atmosphere, 5770 Kelvin. You see that in some places in the infrared, it matches quite well, but there are places where it doesn't match. So we can try a Planck function of a different temperature, say 6000. Now, it matches better at shorter wavelengths, but similarly at longer wavelengths, but still not very good. And then if we use even higher temperature, we get better matches in places, but not in other ones. Now you can notice two things, that a Planck function does not necessarily represent the spectrum of the solar atmosphere, the integrated spectrum. Why would that be? Well, maybe, yeah. I mean, that would be kind of an explanation. But the simplest way to think about is that, again, realizing that opacity varies with wavelength. And therefore, if we look at different wavelengths, we look at different layers of the atmosphere that actually have different temperatures. So it happens to be that at 1600 nanometers, we have a maximum, and that's exactly where the minimum is in the background opacities in the solar atmosphere. The background opacity is a result of H minus. There's a hydrogen atom that captures an additional electron, and it has a large opacity. And this opacity has a local minimum at 1600 nanometers. And that's where you look to the deepest layers of the atmosphere. You see the highest temperatures, and that's why there is this bump here. Right? So the spectrum is not. It's not a good model to represent this spectrum with just one temperature. Right? So we can make an approximate determination of the temperature of the solar atmosphere, but our model is not very precise. Right? So next, I will just go hopefully quickly through just the notation of the radiative transfer equation, so that we can show where the simplification of the Milne-Eddington comes from. So we'll talk about intensity, absorption, and emission, just in more phenomenological terms, the radiative transfer equation, and what the source function is. We haven't heard the term, I think, yet, source function. Then Eddington-Barbier, which is a simple way of saying, well, the source function at a given height gives you this intensity. We'll talk about limb darkening, why we see limb darkening in the atmosphere, and basically the reason is, as you can easily imagine, that the temperature goes down with height. So when we look at more of an angle in the atmosphere, we sample higher layers of the atmosphere, where the temperature is lower. So towards the limb, we see lower temperatures than at this center. Okay? But we'll formalize that more. And then we'll talk about spectral lines. So here is a spectrum, very nice, artificially colored, but the spectrum is a real observed spectrum from with the FTS instrument that was back then at Cape Peak. It shows all the spectral lines, the millions of spectral lines. Some obvious things that we can recognize, for instance, these two. Anyone know? Yeah, I mean, look at the color, right? It's artificial color, but it's more or less realistic. So you look at sodium streetlights, which is a sodium vapor that gets excited and then emits at these wavelengths. That's where that color comes from. These are the sodium D lines. This line? What? H alpha, yes. These three? Think of the color, wavelengths. The magnesium B lines. Yeah, that is just for fun. I like spectra, so it's my passion. So these, in a different representation, you can plot the intensity as a function of wavelength, and these are spectra in two different regions. One region that at the top is the region about the calcium H and K lines. These are the broadest and strongest lines in the visible part of the solar spectrum, even though there's only 1/10,000th of the amount of calcium that there is of hydrogen. There's no hydrogen line in the visible that is stronger. And there's a good reason for that. I'll tell you at some other time. Actually, I'll tell you next week when we talk about non-LTE radiative transfer. And then here again, in the same region as I showed before, these are the sodium D lines in the orange part of the spectrum. Now, you'll just notice as a curiosity that in the blue, there are many more spectral lines than in the red. This is not a solar property. This is just accidental in the sense that there are many more atomic transitions in the blue that happen to be in the red. So that's why there's no, for instance, there's almost no real continuum. It's hard, oops. It's hard to find a place where there's no spectral line in the blue. So when we take an instrument like some of the instruments that Kevin talked about earlier, and we put a slit over part of the solar, we put a slit over part of the solar surface that we image with our telescope, and we take the spectra, you see that the spectral lines are actually not at one fixed wavelength. They are quite wiggly. And of course, you all know that this is basically Doppler shift. There's granulation. And so in bright parts where you cross a granule, you'll have a blue shift because that's where hot material comes up. And then in the dark intergranular lanes, you have a red shift. It's dark and there's a red shift, right? So that's what you very easily can see in a spectral line. There's motions in the solar atmosphere. Then when you take determined Stokes V from this spectral information, you see that also there is some of the velocity effects that you see, but also there is strong variation in places where there's this bright point, for instance. You see that there's much more amplitude in the Stokes V profiles. And of course, this is because there's a strong vertical component of the magnetic field in your line of sight. And this makes the Stokes V profiles much stronger. So again, there, just by having a simple look at the spectrum, we can see that there are strong variations of the physical properties over the solar surface. So now let's get down into a little bit of the little gritty and do some of the definitions. So the intensity that we talk about is the flow of radiative energy at the location here, per second, per wavelength interval, per solid angle. So intensity is an angle-dependent quantity, right? Through the surface of dA, perpendicular to this surface, right? So that's just the definition, nothing special. Then we have absorption. So if there's material in this little slice that absorbs, then the difference between the intensity before it goes through this slice minus the intensity that goes that we have afterwards is a negative contribution. There's some light that is absorbed, and this light that is absorbed is proportional to the absorption coefficient alpha, which is typically wavelength dependent. It's also proportional to the amount of light that falls on it, and it's proportional to the path length across this, right? It's very simple definition. Then similarly, we have the emission. Again, the difference between the intensity before and after is a contribution that is in this case positive, is the emission coefficient times the path length. Yeah. Now, when you combine the two and you put both emission and absorption in the same equation, so you have material in that slice that both absorbs at that wavelength and emits at that wavelength, we can write the equation of transfer in this way. We can bring ds to the other side, and we have j minus alpha lambda. And then if we define the source function as the ratio of the emission coefficient divided by the absorption coefficient, that's a definition, but it's a very useful definition. Then we can write, and we define the optical depth as alpha times the path length, right? We can rewrite this equation in a very simple way. This is basically almost the simplest differential equation that you can imagine, right? But the difficulties in this transfer equation, of course, are not in the mathematical form of this, but are in the microscopic details that contribute to the emission and the absorption, and the dependencies that the radiation field induces in those absorption and emission coefficients. Right? Now, one way to think about the source function is that it is the emissivity not per in the transfer equation, we have the emission as the emission coefficient times the path length. The source function, you can think of the emission per optical wavelength or per optical path length, not geometrical path length, but optical path length. That's the way to think about the source function. Now, if we have different processes that contribute to the emissivity and the absorption, for instance, you cannot just add the source function. You have first to add the emissivities, then you have to add the absorption coefficients, and then you can write the source function as some weighted sum between the source function from the continuum and the source function from the line, for instance. And this weight is the ratio of the two absorption coefficients. Yeah, this is all simple, just what is it? Arithmetic. Yeah, and any questions? Is clear? So now we have the equation of radiative transfer along a certain direction. Yeah, we wrote down this equation along a path length, and we can introduce a formal integration of that. Right, it's just a technique to solve this differential equation. You multiply with e to the minus tau, and you can just integrate on both sides. And so you can write this. This is called the formal solution, and it's called the formal solution because even when you can write down this equation in more complicated situation, the source function depends on the radiation field itself. So this is not a closed equation. This is an equation that typically we have to solve iteratively. And this radiation field is not only along the ray that we are looking, but it also is the radiation field that can come from different places, even very different wavelengths, because when you look at the energy levels in an atom, we can have an excitation in a very different spectral line than we are studying. And that contributes to the excitation and the de-excitation of the line that we are studying. So this is really typically a non-local and non-linear problem. But we can still write this as in this equation. It makes sense. It's just these are the same equations written in a different form. Right? So now we can look at this equation and make a simple approximation. Say we have a slab of thickness d, and this thickness can be very small. And then we look at the approximation. So for instance, if we assume now that the source function is constant over the path length, right? Then we can make this integration and we can write this equation. We can solve this equation. This is the solution. And then when d is small, we see that this will be 0, right? No, this will be, yes, this will be 0 because so then we have this solution. When optically thick is large, then this becomes this disappears, and we only have the source function. So the emergent intensity from a very thick, optically thick slab is basically the value of the source function. The source function is constant in that slab. And you can go through these equations yourself and realize those things. Now, typically in the geometry of a solar atmosphere, we have that z goes up, while the path along the ray that we are looking at is the other direction. So we typically, and this is sometimes a bit confusing, this introduces a minus sign. And instead of ds, we have minus dz. This is nothing special. This is nothing mysterious. It's just the geometry of looking into an atmosphere. And an atmosphere is semi-infinite, right? Because optically depth keeps increasing the deeper you go. So it goes to infinity, basically. So the radiative transfer equation, basically I and S here flip. This might seem a little bit strange in the beginning, but it's just only the geometry where you have this minus sign in the convention. Typically, then, when we look at a different angle at the atmosphere, we have if so dz, instead of dz, we have dz over cosine theta, and so you get this mu on this other side. So that for an inclined ray, so for a vertical ray, mu would be 1, and for an inclined ray, it's between 1 and 0. So again, then when we write the transfer equation for and write the expression for the emergent intensity where tau equals 0, right? For an inclined ray, this is the expression that we have. Now, say that we use a power series in tau for the source function. We can just do that, right? And then using the simple equality here, we can substitute this in here, and we get for the emergent intensity that the emergent intensity at angle mu is A0 plus A1 times mu for the first two terms. So if we assume that the source function is linear with optical depth, then we know that the emergent intensity is the value of the source function at optical depth mu. So at the vertical, in the vertical direction, the emergent intensity approximated by a linear source function is the source function at tau equal 1. This is called the Eddington-Barbier relation. Yeah, this is just simple mathematics using this equality and the fact that we can express the source function as a power series in tau. So if we now have an atmosphere that is hotter in deeper layers and cooler in higher layers, and we look in the vertical direction, and we compare this with the intensity at an angle that corresponds to cosine theta equal mu, then we see that the vertical intensity will be higher than the intensity at an angle, right? Because optical depth unity occurs at a higher layer. So the intensity is the source function at optical depth mu for an inclined angle, right? So IA in the vertical direction is larger than intensity at an angle for an atmosphere that has a decreasing temperature with height. Yeah. So this explains limb darkening, right? The source function, the source function decreases with height. Optical depth unity is in a deeper layer at a higher source function when we look vertically into the atmosphere. When we look at the limb, we look at an angle into the atmosphere. And so we sample a higher layer of the atmosphere that has a source function that's lower, and therefore gives us a lower intensity. And therefore we have limb darkening. So here's a spectrum. We have absorption lines. In a very similar way, we can explain that. And this is a bit of a complicated diagram. You maybe have seen it if you have been to any of the earlier lectures, or if you have been to any of Rob Rutten's talks or lectures. This is one of his drawings. So if we have, so I'll go with it. It looks a bit complicated, but in the end, it's not that hard to understand. So if we have a absorption coefficient that depends on, in this case, it's denoted with mu, but you know that wavelength and frequency are interchangeable because wavelength times frequency is the speed of light, right? So if you have something that changes with wavelength in property, then also it changes in property with different values of the frequency. So if you have a spectral line that has a higher absorption coefficient at its central wavelength than it has in the wings of the line or away from line center, right? Then the run of optical depth with height follows lines of different angles, right? If you have a higher opacity, then the opacity increase or the optical depth increases much faster with going deeper into the atmosphere than at a wavelength or frequency where the absorption coefficient is less, right? So now if you look at optical depth 1 and you have a source function that decreases with height, and you look what is the source function at optical depth unity in the continuum or in the wing of the line, you see that you sample a deeper layer a higher value of the source function. And then when you optical depth unity is much higher in the atmosphere for the wavelength where the opacity or the absorption coefficient is much higher. And therefore you sample a lower layer. And therefore in the core of the line, you see a lower intensity. So it's just simple Eddington-Barbier sampling layers of different temperatures that it makes you get an absorption line. And the opposite, of course, is true for emission line. This is exactly the same picture. The only thing that has changed is that in this case, the source function increases with height. And so all the lines that are in wavelength below 160 nanometers are in emission because they all sample the continuum it goes through the temperature minimum and increases with height in for shorter wavelengths. And so all the shorter wavelength lines in the solar spectrum are in emission because the line core samples a higher source function than the continuum when the source function increases with height. So this is just a function of where you sample the atmosphere. In the deeper layers, the source function, because the temperature decreases with height, the source function decreases with height, you get absorption lines. In the layers where, in the UV, where the continuum is more opaque, the lines sample a source function that is increasing with height, and therefore you get emission lines. So I mean, yeah, this does not say anything about what heats the atmosphere. It just takes as a fact that the chromosphere has a temperature that increases with height, and this is I wish we would know, right? This is what we are doing here. We try to figure out why the chromosphere really increases with height. But if you have a temperature that increases with height or a source function that increases with height, you get emission lines. So for instance, these three lines here, these are oxygen lines, neutral oxygen line, oxygen 1, at 130 nanometers. They're actually very interesting lines to look at. Their intensity, there's a line in the, and this is one of the cases where non-LTE in a different line makes a big difference. For instance, one of the lines in the oxygen term scheme, so the way the energy levels in the oxygen atom are connected by different radiative transition, that one of the lines overlaps with Lyman beta, and Lyman beta is a very intense line, is very strong line. So there's a lot of excitation in the oxygen that actually then the de-excitation causes these lines to be much brighter than they would be if there would not be this overlap with the Lyman beta line. So if you neglect that overlap in the spectral lines, your predicted oxygen intensity would be much lower. Okay, so now let's go to the essence of the Milne-Eddington approximation. So we assume that the atmosphere is plane parallel, semi-infinite, and in LTE. That's actually, I have this here, that allows us to make the connection between what we retrieve from the fit and the temperature. This is actually not a necessary condition, but it allows us to make the connection between temperature and the parameters that we retrieve from the fit of Milne-Eddington. We assume that all line formation quantities are constant with height. We assume that the Planck function over this height that we sample varies linearly with the continuum optical depth, and it's pretty much the same assumption I made to explain to you the Eddington-Barbier relation, right? So we write the source function, which in this case I've assumed is like the Planck function, as a constant value plus a linear term dependent on the continuum optical depth. And this is just a reference wavelength. David talked about this earlier, that typically we take that as 500 nanometers. That choice is what we use, but it's not, that wavelength is not particularly relevant. otherwise. So we have, again, we have the expression for the optical depth in this case. So it's not the optical path length, it's the optical depth because we look into the atmosphere. And it is this minus alpha dz over mu. And we have the source function or the equation of radiative transfer for an inclined ray, generally case. And again, we write the same the formal solution. We introduce this value where the total optical depth is the continuum optical depth plus the optical depth that is the result of some spectral line transition, right? And we write this as a ratio eta, which is the ratio of the opacities of the line, the center of the line, and the continuum, and some normalized line profile times the optical depth in the continuum. And so therefore we can write the source function in this way. Again, just substituting the values that I put here in this way. So we write the source function as this B0 plus this beta, which is the ratio, this coefficient for the linear part, and then the contribution from the line. Yeah. You can just, once you look at the slides, you can just follow this through. Typically in the solar atmosphere, these line profiles, this is a logarithmic plot, so of the Voigt function. So these line profiles are the shape of a Voigt function, and a Voigt function is a Lorentzian profile, which is the natural profile of a spectral line in the frame of reference of the atom. Typically broadened by the finite lifetime, so the natural broadening, the finite lifetime, and some perturbations from other atoms that perturb the electronic states. Van der Waals broadening is one, and if you convolve this Lorentzian profile with a Doppler and what is it, a distribution of velocities that we have in the solar atmosphere, then you get a Voigt profile. And the Voigt profile depends on the normalized frequencies, where the frequency is normalized by the Doppler width. And the Doppler width depends on the temperature and the square root of the inverse of the mass. So typically, hydrogen has a very low mass, so it has a large Doppler width. Heavy elements like iron are have a very small Doppler width, and therefore are much more sensitive to Zeeman splitting, for instance, because we talked about earlier, the sensitivity of a spectral line really depends on the ratio of the Zeeman splitting over the Doppler width. So H alpha is a very poor line for spectropolarimetry because it has such a large Doppler width. And typically you barely see Q and U in H alpha. And then there's the damping parameters. And you see that the shape of the profile is almost independent of the damping width of the spectral line. But the wings strongly depend on the value of this damping width. And these are typical values for spectral lines. Spectral lines in the chromosphere will have a damping width that's comparable to this. In the photosphere, it's more like this. The damping width depend on the intrinsic broadening of the line, like I told you, natural width, which is due to the finite lifetime of the transition, and some of the perturbations of different atoms that perturb the atom in its excited state. So the Doppler profile, again, this Voigt function, which is the normalized profile function, depends on this alpha or this A, and it depends on the Doppler width. And we just use that as a parameter. So when we use this in the Milne-Eddington approximation, we don't really distinguish this. We get one value back for the Doppler width, but we don't distinguish the physical aspects of this Doppler width. So it makes the approximation very easy to use, but it gives us limited use of deriving the physical properties of the atmosphere. That's one of the warnings that the Milne-Eddington effect has, Milne-Eddington approximation has. Now we can put this source function into the formal solution. Right? We can substitute this source function in here. And since everything is constant with optical depth, we can actually write down the solution analytically. Yeah? And so this intensity now depends on, in this simple assumption, depends on 5 parameters: on B0, on the coefficient for the linear part of the source function as a function of continuum optical depth, on this ratio of the line opacity to the continuum opacity, on the thermal broadening, and on the damping width. Just 5 parameters describe a line profile. And this is without polarization. So in the notebook, we will have a chance to play with this. So if you use this formula to calculate line profiles for different values, for instance, here I've varied, varied the damping width, kept these constant, these values constant, and then these are the line profiles that you get, and you just vary the damping parameters A. Similarly, when you just vary the steepness of the atmosphere, you get these line profiles, shapes. So that shows you that if you make the atmosphere steeper, in the gradient of the source function is steeper, you'll get deeper spectral lines. This is one of the reasons why, for instance, spectral lines in the center of a granule are deeper than in the intergranular lanes, because in the center of a granule you'll have you have hotter temperatures at the bottom, but the temperature changes much faster with height than in the intergranular lanes. So in the intergranular lanes you have shallow line profiles that are typically redshift, while in the granule centers you have deeper lines because the gradient in the source function is steeper. So if we vary the thermal width, you see that the width of the line changes strongly, right? Again, the narrow lines are more similar to lines from heavy elements like iron, for instance, and the broader line profiles would be more similar to spectral lines that you see from lighter elements. So as again, points to take away from this is the Milne-Eddington assumes constant properties with height. So let me actually go back one more thing. So now, so that we know that now a spectral line profile depends in the Milne-Eddington approximation depends on these 5 properties. So now when we have a observed line profile, we can fit this model spectrum to the line profile, and by doing a multivariable fit, like 5 variables at the same time, and if we find a solution, then we have these 5 values that are derived from the observed line profile. Right? This is just a very simple function fit, nothing else. It doesn't involve any radiative transfer. It's just a mathematical method where we make the best fit by varying all the parameters and get the best fit to the observed line profile. And that best fit, that may be, sometimes it's degenerate. Sometimes there's not one solution to this. You can imagine that some parameters, if you change them, they change the line profile in different ways and you cannot distinguish them. But if once we have a solution, we get values of all these 5 parameters, and it will tell us something about the atmosphere. It will tell us about basically if we say, well, we have B0, that we relate that to the temperature, the average temperature of the slab that we look at. We have a value of beta, which is the slope of the source function with optical depth. We have a value of the line strength, and that means that since we know what line it is, we have an estimate of basically the population numbers in the line. We have an estimate of the thermal width, so we know how the line is broadened, and we have an estimate of the damping width. So, as I told you before, it's really hard to make exact physical inferences of the atmosphere, but at least all of these things, and if we make a map of any of these parameters that we derive from analyzing the spectral profiles over this whole map, we get an impression of how the atmosphere varies in different properties. The Milne-Eddington approximation allows an analytical solution of the transfer equation, and therefore makes what we call forward modeling very fast. We can calculate analytically the shape of a source function given values of these 5 parameters. Right? We don't have to solve the radiative transfer equation. We basically solve the radiative transfer equation by deriving this analytical expression for the line profile, by assuming that the source function and all the other properties of the of the line profile are constant with height. So this is ideal for very fast inversions, but with the caveat that they give us somewhat limited information about the properties of the atmosphere. So it's a strong simplification of the radiative transfer. And then again, even if you fit the observed profile perfectly, there's an error, of course, that you make the assumption. Typically, quantities vary with height in the atmosphere, and you've assumed that they're constant. If you compare 2 lines, they typically give you information from different height, so they are not directly comparable. If your observations have 2 lines and you make a Milne-Eddington solution from one line and you take a Milne-Eddington from a different line, then you'll have, it's hard to compare them because they give you information from different lines in the different heights in the atmosphere. While if you do a more involved and sophisticated inversion like SIR, you get a coherent picture of the whole atmosphere where you have a self-consistent variation of the properties with height. So, do we have time? Where are we? So I think it's just a few slides, and it will just add polarization to the. So let me just add 5 more minutes, and then because in principle the exercises don't involve polarizations, so we could stop here. But I think since we're talking about spectropolarimetry, it's useful to just go one step further. And so, I mean, we've seen all the properties, right? I don't have to really. So the most essential point is that with the knowledge is how polarization is generated and transported in the atmosphere, we can infer the properties of the atmosphere by knowingly analyze the shape of spectral line profiles, right? We know the forward problem, and then we can say, well, we can go the other direction. We know how the properties, how the strength of the magnetic field, how the velocities, how the temperatures affect the local properties of the absorption and emission in the spectral line, and how that affects in the end the emergent spectrum. And then we can say, well, we now see a certain emergent spectrum, and we can then infer the properties of the atmosphere. That's the idea of an inversion. So instead of the linear linear transfer equation, we now have a transfer equation, like David has shown, that is basically a matrix equation with 4x4 quantities, the Stokes vector, the absorption matrix, which is a 4x4 matrix, and the emission, which is a 4 vector. And then this absorption matrix has this shape. David showed all of this, where this comes from. And he showed also how the absorption and profile is affected by Zeeman splitting and line of sight velocity. And he showed that the Zeeman splitting is basically a linear function of the magnetic field, and is also inversely proportional to the Doppler width. There's the broadening velocity and the Doppler broadening. They are all the same as in the unpolarized case. The only difference is this. And so now, this is just a plot of when you vary properties of the magnetic field strength and how the line profile changes. I won't go through that. It's interesting, but so this is a shape of a spectral line actually through a MHD simulation. And you see that this line is at 1.5 micron, so it is close to this 1.6 micron when we look deep in the atmosphere. So this line gives us information. It's interesting for two reasons. It gives us information from deep in the atmosphere because it forms so deep, and it also is far in the infrared, so it is more sensitive to the Zeeman splitting, because the Zeeman splitting is, as you know, is proportional to b squared over the Doppler width. So it goes with the wavelength linearly. We can similarly use the Milne-Eddington approximation on the polarized radiative transfer equation, and we get an expression for the line profile. And even though it's much more complicated, we now have a line profile that instead of 5 parameters depends on 8 free parameters. So we can still do a fit to all the Stokes profiles and derive these 8 parameters and get an expression for the magnetic field strength, the inclination, the azimuth, the damping width, the Doppler width, and the source function parameters and the line ratio. It's almost the same as the unpolarized case, except we have more free parameters, and so the fit becomes a little bit more time consuming, but it's not terrible. So we can do it in the same way. So I think this is what I had for. Let's see. Yeah. So don't need to do that. So any questions? Okay. Yes. Yes. So I think there's no substitute for trying things out yourself. I mean, I can show you all the things and I can talk about them and ad nauseum, but I think getting your hands dirty on these things and take the notebook, or maybe not now exactly, you can just follow along initially, but getting your hands dirty, play with the different things, and notebook is very convenient for that, and see how it changes the line profile, how, for instance, we will take a map that is observed with Inode and fit some line profiles. You can use different locations in the map, see if you get similar fit. Maybe I just, or Ivan in this case, who made the notebook, we just picked a pixel that looked pretty good. But there might be pixels that don't look as good, where you can't really get a fit as closely as those. So get a feeling for that. Really take the time in a little bit of your off time, or later when you go back home. Go through the notebook, change some things, see how it affects things, get a feeling for what happens. I think that's the best way to learn. Okay, so we'll be back in half an hour or so. Okay, yeah. Okay. Yeah. Start again. So let me ask, since it's the first time we do this, who has never used a Python notebook? Everyone has? Oh, okay. That's really nice. So this, I mean, it's interactive. I will just go through it so that we just accentuate some of the points I made, I think, but we won't. Again, I think it's better if you, for this first time, that some other time you go and change things. Well, maybe we'll see how it goes. If it goes well, we may just do a few exercises live and let you experiment, and then you can report on what you find. We'll see how it goes. This is a Python notebook that was created by Ivan Milic. Ivan will join us next week. I think he's coming in on Friday. He was unfortunately got sick just before he was about to leave, but he will be talking about Handler polarization next week, and he's always eager to discuss all the kinds of radiative transfer problems. So next week we indeed do engage him and pick his brain about all these things. So this is a very nice notebook. So I put the it's the same equation I had in the slides, right? This is the expression that we get by making the Milne-Eddington approximation and doing an analytical solution of the transfer equation. Oh, yes, I guess we can. There is somewhere. Oh. Control plus.
It's in
Oh, there you go. Perfect. Thank you. But that's more readable. Yes. It's like Google. I say something and it works. Okay. Thank you. So we're just basically putting this equation in the Python notebook and experiment with it. So first we define how to calculate a void profile. S1 is the slope and S0 is the constant value. Yes, yes, yes. And I apologize. I sometimes call them S and I sometimes call them B, because and the difference is between this is more general. I don't have to necessarily. It's not essential for the Milne-Eddington approximation to say that the source function is an LTE source function. So it's not necessary for the approximation to assume that the source function is directly related to the temperature. Right? It's just a source function that has a constant plus a slope. And what that physically means, you'll have to decide afterwards. At this point, it does not have necessarily a physical meaning. So what Ivan does here is so let's see if we can run this. I'm sorry if does it? No, let's see. No, I see. How do I shift enter? Okay. Okay. I learn something every day. We define a source, the void function. So this is just a function definition that as a function of the frequency, we have what does it? So it's okay. Well, it's not that important, but the void function goes. Where do we go here? No, I'm sorry. Can we? Yeah, we can do that. So basically, we call the void function with the central wavelength, the Doppler width, the damping, and the wavelength grid, and it gives us back the void function as a function of those parameters. So let's do that. And so now we are a bit of a trouble because it's the big size. So we calculate different spectral line profiles with different central wavelengths, different damping width, and different Doppler width, and they're all parameterized, so they're all unitless values in this case, and the same wavelength width. LL is just a linear wavelength grid between 6301 and 6302 with 200 wavelength points, 201 wavelength points. Yeah. And these are the spectral, the absorption, the void profiles that you get from those parameters. So now we define a function that's called ME scalar, Milne-Eddington scalar. That is a function of the P, which is just I guess in Python you call it a tuple, right? With these 5 parameters, and they're passed through the one parameter P, and then the wavelength grid. And what this does is just it actually calculates the line profile as defined in the top of the notebook. So let's try that out. So we define all 5 parameters. We define a wavelength grid, and then we calculate the spectrum with those parameters, and we plot it. So now we have a nice spectral line that is normalized at a continuum intensity of 1, because we used unitless parameters. Yeah. So now we make a plot, and we vary some okay. Where? Oh, okay. Yeah. I don't know how that got there, actually. Okay, that must have just been a mistaken click. Okay. So we vary now the slope of the source function. Yep. So in the blue line, very interestingly, if we have a medium that has a constant source function, we will not have a spectral line. Right? We can understand this now because we don't have the line core forming at a different temperature than or a different source function value than the line wings or the continuum. So this immediately tells you that the reason we have absorption line is not because we have more absorption in the line center, because the opacity is larger, but it's really because we sample the source function and we sample different values typically in the real world. But if we have a medium that has a constant temperature and the source function is flat with height, then we don't have a spectral line. We don't see the spectrum. So again, I would encourage you to experiment with this. You can do it now or you can do it later. But if we calculate the line profile with different slope, that we see how steeper we make the line, the source function, the deeper the line profile. For the rest, the shape is the same. Right? It's just the depth of the line changes. So now we change the width of the line, the Doppler width, and we get these line profiles. So again, this is similar to more or less thermal broadening, where the thermal broadening can vary not only with the temperature, but also the mass of the atom that you're looking at. Right. And you see that you get something that the wings are mostly affected by, like the line core intensity doesn't change, right? It's really, but all the shape of the line changes as well, because you get more or less saturation in the wings. It's like the curve of growth effect. Now we change the damping width, and so here is how the shape of the line changes. And so if we increase the damping width, we typically mostly increase the line width, but the line core, the shape of the line core is very similar. That's characteristic of the void profile. So I should run these. Oh, I skipped one, I guess. I have to start all the way. Let's run through them. We did have this works. Okay. Yeah, there you go. So here we change the ratio of the line center opacity or absorption coefficient over the continuum absorption coefficient. Right. So this basically a parameterization of the line strength. And so that you can see that drastically changes both the shape of the line. You get kind of a saturation in the line core if you make this eta very big. And it really changes the shape of the line. So this now starts to look like almost like an H alpha profile with a very flat bottom. And you can imagine that you have a flat bottom when the opacity in the line core is very high. The line core height changes very little when you change wavelength, and so you almost see the same source function value. Which is what happens in H alpha, where the source function is almost flat for different reasons. So here we change the constant value of the source function. Again, you see the effects on the line profile. Oh, this is the slope. Sorry, not the. Yeah.
what happens if you put a slope which is negative?
Slope that's negative.
Mhm.
I know you get an emission profile, right? Yes. All right. Sure. If you put a negative slope, then you have a source function that increases with height or decreases with optical depth. Right? So you should get. Well, try. You have the notebook. You can try. Guys can try. See if that's. Huh? Yeah. So try that. So change the slope. Very good suggestion. Change the slope and see what happens, and see if just change the sign, and see if indeed you get a and report back. Yeah, it works. Good. So here it shows that when you have an understanding of the physical or the how the equations work, you can make a prediction, and also when you see something, you can interpret it, right? If you have you see a emission line, now you know what is the physical reason for that. So the doing this kind of games or playing with these equations gives you a feeling of what is possible and what happens. And when you now next time you see something of a line profile, you see how a line profile, for instance, varies over the surface. It tells you something about what quantity really varies about this across the surface. If you see a line profile that has more or less the same shape, but that varies a lot in line depth, you know that the slope over the surface changes. If you see something, a line profile that in some places has wings, in some places doesn't have wings, it tells you something about the Doppler width and the variation of the damping width. Now, with the Milne-Eddington, can you interesting. So you all know the shape of the calcium H and K lines, right? So they have wings, the intensity goes down. Then you have the K2 features, where the intensity goes up and then it goes down again. How do you explain that? It's not an emission line, it's not an absorption line. And can you reproduce that? Could you try to fit a line profile like that with a Milne-Eddington? Would that make sense? So you would need a source function that first decreases, then increases, and then decreases again, right? So no, we cannot represent this. It does not make sense to analyze the calcium H and K lines with a Milne-Eddington because we don't have a source function that is linearly dependent on optical depth. We will get next week, we will see why the shape of the source function is like it is. And it's because not necessarily the temperature sensitivity, but because higher in the atmosphere, scattering becomes important and the source function drops down because actually you start to see the atoms, the radiation field starts to see outer space. And so radiation field gets lost and it falls below the Planck function. And so the source function drops again with height. And that's why you get this very peculiar shape that you only see in calcium H and K lines and magnesium H and K lines very similarly. So this shows you that you have to be careful with the model that you choose to analyze your data, right? You cannot, you know immediately now that you have a source function that first decreases, then increases, decreases again. You cannot use on a line profile like that, you cannot use a Milne-Eddington approach. That doesn't make sense. Or you'll never fit the line profile. So everyone finds emission lines? Okay, good, very nice. Did this. Okay, so I hope everyone was able to, this is a pretty big file, but to download the FITS file as well. And if you make a plot of the data cube at one wavelength, this is how it looks. Right, you can see the granulation. You can see brighter areas that are like small magnetic field concentrations. And then this is a plot of the Stokes eye so we should go there. Yeah. Of Stokes eye in 1 pixel, and you see the two iron lines. Compared to what you're used to from when you look at the telluric observation, what is missing here? Typically, when you look at this, there's 4 lines here. No? Yeah. Yeah. So typically there are 2 oxygen lines that are here, here, and here, and you can, in a spectrum, you can always easily recognize them. Because they're very narrow. Because the temperature in the Earth atmosphere is much lower than in the sun. Right? But B, they don't show any Doppler shifts. So if you take a spectrum along the slit and you look at the lines, you see that they are constant in wavelength. So that makes it easy to recognize telluric lines. But they are a pain, of course, because if you fit line profiles, you have to ignore them. But yeah, this is an observation from Inoda, which is in space, and there's no atmosphere there. That I need not enough to absorb anything. So the telluric lines are absent here. Did we miss something? Oh, did I? Oh, there's a problem in the. I think I didn't read properly because there's something happened here. Okay, so now. Oh, now I haven't changed. I thought I had changed it in my. Okay. I'm not at my computer, so I don't know off the top of my head where it is. I think I know. No. Oh. see if that. No. I don't remember. Can I? Could you? No. See what directory I am in. My. Can I? Sorry. Yeah. Oh. Can I even? Yeah. Yes. Okay. Yeah. Oh, August 22. Okay. Yeah. Can you open it again? Yeah. Yes. Yeah. Yeah. That was good. Yeah. Yeah. Okay. That works. There we go. So to analyze the spectra in a uniform way, we first divide the spectrum, all 4 Stokes parameters with the continuum intensity, the first 10 wavelengths, the average of the first 10 wavelengths. That's what the box 26 does. Now we assign a wavelength scale and then plot the spectrum in a normalized intensity. See, it's close to 1 in the continuum. And so we plot again just 1 pixel. And now we import a minimize function, which is just a routine that tries to find a fit by varying the parameters that I give it. And then you can give it some starting parameters that are close, so that it doesn't spend endless time finding the solution or get lost. And then giving that, you just minimize the difference between the observed profile and your calculated profile to find the parameters, right? And in this particular case, for the Stokes profile before that we used, these are the values of the 5 different parameters below. And you can see that the line profile fits pretty well. It finds a good fit. And then, so here is where you can start to play and try different locations on the map and see if you can find similar fits for other locations. And let us know if you find something that does fit or something that doesn't fit, or you find something strange. Anyone have any interesting line profiles to share or fits or? Huh? You have a question?
Well, more than a question, it's a little bit to start a little bit of discussion. When you showed at the very beginning, when you vary one parameter and you see how the line responds, and then you
Yes.
vary another parameter and you see how the line responds.
Yes.
There's a lot of similarity in the responses to some of the parameters, at least within
Correct.
certain regimes.
Sure.
Like look at the eta 0, for example.
Yeah.
For the first few values, the blue, the orange, the green, and so on, the line just increases in depth.
Yeah.
If you look at the response to the source function gradients, you see something very similar.
Sure.
And from there, well, do you want to talk a little bit about degeneracies?
Yeah, so that's what you would call a degeneracy, like that there are solutions of different combinations of parameter that would give an equally good fit. And how do you distinguish between those solutions? And just using the what we have, there's no way of distinguishing. Some of them maybe you can physically exclude because they don't make sense in other ways. But mathematically, you cannot distinguish between those solutions if they give equally good fits. Or fits that have a chi-squared, which is a measure for the difference between the observed and the model profile, then you have no way of distinguishing between those. That's why you call them degeneracies. This is a general problem in kind of spectral inversions because it's in some ways an ill-defined problem. There are these sensitivities that work in similar ways. Do you have any other things? I mean, you will talk, or maybe David, if you have. Yeah. Yeah. And this is a practical problem, right? There's just no way of in a sense, our problem is not completely well stated. Yes, David, you're gonna get me in trouble.
It's just a question just to try get discussions, okay? What should I do if I want to fit just the two lines, the two iron lines, because I have two?
Yeah.
But the Milne-Eddington is just for single one or what?
Yeah, I mean, basically in some way you are not having a self-consistent solution, right? Because you are finding values that are not, you cannot, I guess you could fit them. Well, you would have to rewrite the fitting procedure to fit them at the same time, but you make the assumption that the atmosphere is constant but you're sampling different heights, so you violate the principle that or your assumption. So you don't get physically consistent results, I would say.
And actually, I do agree, but you know that we do fit both lines simultaneously.
Yeah.
Because they are lines pertaining to the same multiplet. So the line to the line to continuum absorption coefficient is related with a constant factor between both lines.
Yeah.
So you could fit both lines with a single Milne-Eddington model.
Yeah.
Actually, and
but they form in different heights. They're not equally strength. Yeah. Yeah. But yeah, in principle you can just add them and fit them at the same time. Yeah. Can you use the microphone so that we can also record it?
So even though the lines are different, forming at a different height, they share the same source function. So we can say that these two parameters can be shared between lines, right?
Well, they don't necessarily have the same source function. If they form at different heights, they have different temperature, and these are LTE lines, so they have different. They don't have the same values of the source function. So if you fit them at the same time, you can imagine that you fit some average of the value spanning that range of heights. So it makes sense at some level, because you derive some kind of average value for the whole range of height, which is typically a larger range of heights than you would with just sampling one line, if you fit them at the same time, with the same source function shape. If you fit them individually, you may say, well, I sample different heights, so I actually, you could infer if that is consistent with the source function. That would be an interesting experiment. You can fit them individually. You'll find a slope of the source function, and you can see if that slope of the source function makes sense with the values that you get from the individual lines. So there's definitely a lot of things that you can learn from playing with this, but you have to be really aware of the assumptions that you make.
I just wanted to note, just for people that work with Hinode data and maybe the inversions that are provided in the official pipeline, that's a Milne-Eddington inversion of the two lines simultaneously with the same atmospheric model for the two lines, or almost the same. We can talk about it, but that's what we do in practice for Hinode, for instance. And yet the results that you get, the formation of the two lines is not identical, so you can't expect the same model parameters for both lines. But for the most part, let's say it's a decent enough approximation within the context of a Milne-Eddington.
Just to comment that this is the case when you have optically thick lines, actually, okay? But when the lines are optically thin and you have several of them, like is the case of the helium 1030, then you can really couple the three lines because they are from the same multiplet, and the source function actually there should be the same because they are supposed to be formed in the same place, isn't it?
You have to be you have to be careful with calling a line optically thin, because no line is optically thin, or no wavelength is optically thin. Maybe the line contribution you can call optically thin, in that the contribution of the line component to the total opacity is less than optical depth, optical path length 1. But the opacity at any given wavelength in the solar atmosphere goes to infinity, or the optical depth goes to infinity, right? Just means that in 1030 you have a significant contribution from the photosphere as well. So I would, yeah. Can use the.
Probably get confused at some point, but about this relationship between the two contribution of the opacity and the continuum on the line, can mention the saturation case. I mean, what this means this, and then if you change the slope, you can get deeper, but here you can like give some explanation about.
Yeah, so when you have a very strong line, so the opacity in the line core is very strong compared to the continuum. How to explain that? I have to think about that. Then a variation in the wavelength gives you a very small variation in depth. And then you almost see the same source function for different wavelengths. Yeah. Okay.
Go back to the equation that on at the very top.
Okay. Yeah. Yeah. Sure.
Since you have a huge eta,
Yeah.
basically at the line core, whatever you change the wavelengths,
Yes.
the second term is zero,
Yes.
vanishes. It vanishes
Yes.
because you have a huge eta. So at the line core, you just see the S0, which is 0.5. You're varying eta, but since eta is huge, at the line core, the second term vanishes, so you only see the first term, which is 0.5. So at the line core, you just see
Which is
the
well, I mean,
intensity
if you-
is close to
but if-
0.5.
But if you think about it, that's the same explanation.
What?
I mean, if you think about it, that's the same explanation. You just explain it in the
Yeah,
in the formula. Right?
yeah.
So basically, what he's saying that unless phi becomes very small, you go further into the wings, then the second term doesn't matter. You don't see the slope. You should just see the S0. And that's how in the formula it's easy to explain. But it just means that the variation of the source function over the line profile is very small. Right? Unless you have a phi that's small enough to compensate for the huge eta. Yes. Well, we are recording, so that helps.
So in inverting measurements to extract physical values for a three-dimensional entity, you have the conundrum that you're making assumptions to be able to do the inversion in the first place, but you also have imperfections in spatial resolution, in time resolution, and in spectral resolution. And that is, I think, the very reason why it is so important to kind of push the boundaries of the various post-focus instruments, whether it's a Fabry-Perot or a classical spectrograph or whatever other crazy instrument people will be thinking about in the future. It is because they have a different mixture of imperfections that this will give you clues, sort of how bad you're doing.
Yes, yes.
That was my comment.
Yeah, no, sure. And it also adds to that you really have to be aware of what your instrument does and what your methods do to know that what kind of errors you potentially make.
Yeah, and nobody can claim with these imperfections that they have the better instrument. We need them all.
Sure. Yes. No, one of the things, so when I first started giving people our age and people were, the most frequent question I always got, what is the formation height of this line? And then people would always, I would tell them, well, you can do this and this, and then they could come back and it's they found 375 kilometers, right? That's a nonsensical answer if you think about it, because that value is really, I mean, it depends, of course, on the method that you say, well, how do you determine formation height? But that value also depends on the model. It depends on the atmospheric model that you use. If I use, you probably all know the VAL models. If I use a VAL C model or I use a VAL P model, I get a different formation height. Right? It's not you have to think about more carefully about those kind of things. And also, to put it in 3 digits is a nonsensical way of putting it, because you have so many uncertainties. The range of height that contribute to a certain intensity is a few hundred kilometers, is a few scale heights in the atmosphere. So you don't get one particular height, you get a range of heights, and it's one value plus or minus 100 kilometers or so. So I think we should probably close the day, right? And leave you with fun things to do if you want. And again, I would urge you to take advantage of those. And we'll come back tomorrow and dig further. If there are no more questions. Okay, thank you.